Hi students, jaldi everybody join the chat. We are live with the first session of organic chemistry right now. Hi everybody. Hello. Hello Vineet. Hello J Siddharth. Hi Raman. Everybody welcome to the session. Just let me know if you can see and hear me clearly so that we can begin with today's session that's going to be jam filled, right? Hi. Hi Pratiksh. Okay, so many people have joined us. Good afternoon, bacha. Hi. Hi Raman. Hi Shaji. Okay. Okay, we are live. So what are we going to do in today's session? So first of all, who all are watching, please like the session, share the session with your friends so that they can also join in. Right now, I'm going to teach you today haloalkanes and haloarenes plus alcohols, phenols and ether. Okay, I know that chemistry exam is just around the corner. So this session is based for your chemistry exam specially. So whatever we're going to learn today is going to be just from the NCERT. What I've told you, I've only added a lot more things that are required from the NCERT in order to answer more and more questions. Just let me know if my voice is clear. If you can hear me clearly, then we can start. Good afternoon. Okay. Yes, bacha, I will make you complete organic today. That is my promise because right now on Sunday, your organic will be just as good as your physical and inorganic that Nabamita ma'am told you. Right, taught you? Okay, yes, bacha, we will be able to complete. Let me switch on the AC because it's really hot here. Really hot. Okay. So I have included screenshots from the NCERT and I will only teach you a little bit more than the NCERT, like what is the stereochemistry of the reaction, what will be the exceptions to the reaction, and sometimes in your NCERT, what is happening, bacha, your questions are directly asked without explaining the reactions in the theory part. So what I've done, I've included even those reactions which are even in example or anywhere in form of just a reaction is given in NCERT, right? So I'm going to explain even those reactions to you. So this session is going to be approximately 2 to 2.5 hours. That's it. And you're going to complete these two chapters with me. So let us begin. Chalo, everybody. Louder. Is it better now? Can you tell me? The mic is right in my face. Is it better? Is it better? Please let me know if you can hear me better so that we can start. Easy peasy. Hi, Rudra. And also, just to tell you guys, if you're also preparing for the JEE advanced or even your JEE mains second attempt and you are looking for resources to do questions from, to do all the PYQs from, which have all the PYQ solutions and everything in just one book, then you can get that book from the link that is in the description box below. If you are interested and are looking for resources, then that's just a help from Vedantu to you guys. And without doing further ado, let us begin the chapter, which is haloalkanes and haloarenes. So I'm going to be teaching you from the very basics, bacha. So we are going to start from the very basics. Even if you know anda about organic chemistry, I'm going to teach you the entire organic chemistry. Number first chapter, haloalkanes and haloarenes. Number first slide is on your screen. So bacha, how do you prepare alkanes, haloalkanes from alkanes? So what do? This is the structure of alkane, right? What is an alkane molecule? This is an alkane molecule looks like, and to create a haloalkane, I just remove this H and I replace it. I just remove this H and I just replace it with a what? Halide atom, right? So just like this, an halide atom will be placed here. So this is called a haloalkane simple structure. So what will be the general formula of haloalkane now? It will be CnH2n plus 1 and here will be the X. X can be anything. X can be your chlorine, your bromine, your iodine and even your fluorine, right? So this is how you do haloalkanes. Okay? Now the next thing, haloalkanes, just like haloalkanes, you can even have haloarenes. Haloarenes are, bacha, what? Whenever a halogen atom is attached to the benzene ring, just like this, I have attached a halogen atom right to the benzene ring is called a haloarene. What it is called? It is called a bacha haloarene. Remember this thing. What is the difference between these two? The carbon atom here, which is attached to the halogen, here it is sp3 hybridized in the haloalkane. Remember this thing. And in haloarene, the carbon atom which is attached to your halogen atom is actually sp2 hybridized. These are the basic differences from haloalkanes and haloarenes. Right? Now let's move on to the second part. So this is again a screenshot from your NCERT where some uses of haloalkanes is given. For example, chlorine is used in antibiotic. I've highlighted the important points. You can just go through that and no need to read NCERT once again after the session is over. Okay, chlorine has an antibiotic like chloramphenicol, right, which is used to treat typhoid fever. Our body produces iodine, is produced in our body in a hormone called thyroxine. Okay? Otherwise, if the iodine in your body goes down, then you can develop goiter disease. This is a screenshot from an NCERT, can be asked in MCQs. All these questions like goiter is caused by the deficiency of which element? So the answer is iodine, given in your chemistry textbook. Next is chloroquine, is again a haloalkane compound which is used to treat malaria. Halothane is again a haloalkane compound which is used as an anesthetic during surgery, and certain fully fluorinated compounds are used as potential blood substituents. Everybody is understanding this? Okay? Yes. Next question. Next we come to the classification of the haloalkanes. Okay, so how do we classify? There are many bases. Number one basis is on the number of halogen atoms attached. For example, if only one halogen atom is attached to the entire molecule I'm talking about, if to the entire molecule one halogen atom is attached, it is called a monohalkane. If to the entire molecule two halogens are attached, it's called dihalo. Similarly, it is called a trihalo when three kinds of halogen atoms are attached. Everybody can see that? Now next is, similarly we can classify the haloarenes. What are haloarenes? When one halogen atom, two halogen atom, three halogen atoms are attached, it is called monohaloarene, dihaloarene and trihaloarene. Okay? Everybody is understanding this? Okay. Next is, bacha, the classification of monohalo compounds. So the monohalo means what? Where only one halogen atom was attached. It is again classified on various bases. Okay? Various bases. सबसे पहला, the number first is the sp3 hybridized CX carbon. Why? Because we're talking about haloalkanes. So the carbon to which the halogen atom is attached will always be bacha sp3 hybridized carbon. Remember this. Okay? Now the alkyl halides, the monoalkyl halides can be classified as primary, secondary and tertiary halides. How do we know that? Bacha, in primary, the carbon atom which is attached to the halogen, remember this thing, the carbon to which the halogen is attached will be attached to just one more carbon atom, then it's primary. For secondary, the carbon to which the halogen is attached will be attached to two alkyl groups, right? And the carbon for the tertiary part, the carbon which is attached to the halogen will be in further attached to three alkyl groups, hence it is tertiary alkyl halide. Everybody is clear on this point, because the basis, the distinction on this, questions based on this is ASIC, identify which is the tertiary alkyl halide. So all these classifications are very important from your board's perspective. Okay, next is again the allylic halides. Allylic halides also have sp3 CX bond. CX is carbon halogen bond. The carbon is sp3 hybridized, right? What are allylic halides? Whenever the halogen atom is attached to the carbon which is directly next to the sp2 hybridized carbon. Can you see that this is sp2 hybridized because this contains the double bond, right? So that the carbon right next to the sp2 hybridized carbon is the sp3 hybridized carbon to which the halogen atom is attached. Correct? Next is again the allylic halides over here. And the next is, this is again a allylic halide, this is again a allylic halide. But can you see that this is a primary alkyl halide? Because this carbon is attached to just one more carbon. Similarly, this carbon is attached to bacha two alkyl groups. Can everybody see? Hence, this is a secondary allyl. And similarly, this one is attached to three alkyl groups. Hence, this carbon is a tertiary allylic halide. Remember this thing, allylic halide. This is a tertiary allylic halide. Is everybody getting this point? Is everybody getting this? Now next, this is how, again another more examples which are given in your NCERT. This is a allylic carbon. This carbon is sp3 hybridized, attached right next to the sp2 hybridized carbon, and the carbon contains a halogen. Hence it's a allylic carbon. Correct? Now you should know these distinctions. Similarly, this one is also the allylic carbon to which the halogen is attached. Right? Next are benzylic halides. What are benzylic halides? People have confusion between two things. Number first is benzylic and number second is arylic. What are the difference between these two things? Arylic halides are those when the halogen atom is directly attached to the benzene ring. Can you see that the halogen atom is directly attached to the benzene ring? This is a aryl halide. Remember this thing. Whereas this benzene ring, can you see here, the halogen atom is actually attached to the methyl group which is directly attached to the benzene ring. This bacha halide, this kind of halide is called a benzylic halide. Again, benzylic halides can again be bacha of primary, secondary and tertiary kinds. What are primary benzylic halide? Can you see that this is attached to just another carbon? This carbon is attached to just one more carbon. Therefore, it is primary. Now, the carbon attached to the halogen is attached to number 1 and number 2 carbon. Hence, it is secondary benzylic. And similarly, this carbon is attached to number 1, number 2 and number 3 carbons. Hence, it is a tertiary benzylic halide. Is this thing clear to everybody? Is this thing clear to everybody? But beta, this session, I'm going to complete 2 chapters within 2 to 2.5 hours. I will not take much more time than that. Okay? Now, next is compounds containing sp2CX bond. We are going to complete each and every line from the NCERT. That is a promise. Everybody who attends my session already knows that happens in my class. Each and every line is covered in the sessions, right? Now, the next kind of halide is when the halogen atom is attached to the sp2 hybridized carbon. What are its examples? The first example is called this kind of bond. This kind of bond, it is called a vinylic halide. What it is called? It is called a vinylic halide. Remember this thing? This is called a vinylic halide. Whenever the halogen atom, can you see that this carbon bacha is sp2 hybridized because there is a double bond here. So whenever a halogen atom is directly attached to the double bond which is a sp2 hybridized carbon, it is called a vinylic halide. Remember this. This is called a vinylic halide. Similarly here in the benzene ring, the aryl halides that I have been telling you, the aryl halides here again it is sp2 hybridized, right? So the aryl halides are also your sp2 hybridized halides. Is this thing clear to everybody? Is this thing clear to everybody? Yes, I am going to tell you what are gem and vicinal dihalides. Just wait for a moment. Now we're talking about the nomenclature of alkyl halides. Every year questions are asked from the nomenclature, whether you're preparing for JEE, whether you're preparing for your boards exam, nomenclature is always asked. So how do you know the name of the compound? So bacha, how will you write the common name of the alkyl halide? You will just write whatever halide is there. For example, if it is made up of 3 carbons, right? And here a halogen atom is attached. So you will call it alkyl halide means what? You will call it propyl halide. Simple. Ho gaya? Propyl halide, simple. And the IUPAC name will be haloalkane means what? The IUPAC name will be halogen. If suppose this halogen is a chlorine, so it will be chloropropane. This will be the IUPAC name. Everything's clear to everybody? So I'm telling you the very basic of the things. Even if you do not know these things, we're going to start from the very, very basics. Now look at this nomenclature given in your NCERT. You should know the common names as well as the IUPAC name of all these compounds, plus all the examples that are given in your NCERT, correct? So the common names are extremely simple. This is a N-propyl bromide because it is a normal propyl, right? And this is a isopropyl chloride. This one is a isobutyl. Can you see? Here the methyl atom is at the second position and the chlorine is at the terminal. Such kind of common name is given to this is isobutyl. This structure is called bacha isobutyl structure. Remember this. And to the isobutyl structure, you have attached a chlorine molecule, so it will be isobutyl chloride. Okay, everything is clear to everybody. Now the common name of the aryl halides. The common name of this is bromobenzene. The bromine is attached to the benzene molecule, hence bromobenzene. Now next here again the bromine is here. Two bromines are attached and the other bromine is at the meta position. Is everybody clear about the position? This position is called the ortho. This position is called the meta and this position is called the para position, right? Because the bromine is attached to the meta position, so it is called meta dibromobenzene. And this the common name of this compound here, bacha, is actually symmetrical tribromobenzene. Can everybody see this? Okay, symmetrical tribromobenzene. So please revise all these names. The IUPAC and the common names are given here. I'm moving on to the next slide because I consider that nomenclature is something that is taught in the 11th standard itself. So I am not wasting more time on this subject right now. Okay, just brush up the concept, just revise for you. I was just revising it for you so that you remember all the things in your head once again. Now these are the two new kind of halides that are in your course. So bacha, whenever two halogen atoms are attached to the same carbon, can you see that two chlorines are attached to only one carbon? Such kind of halide is called a geminal halide. Remember this name. This kind of halide is called a geminal halide. And if the two chlorine atoms or any two halogen atoms are attached right next to each other, can you see? Right next to each other on single carbon, then such bacha halogens are called, such halides are called vicinal halide. What are they called? Vicinal halide. Remember this thing, vicinal halide. Okay, everybody understood this? This is called vicinal halide. Then you should know how to name geminal halides and vicinal halides. So what is the name, bacha? Here the geminal halides are actually named like this. First count the number of carbons. How many carbons are there? Number 1, number 2. So ethyl will come, right? For 2 carbons, ethyl will come. Now because we are naming the geminal dihalide over here, so here it will become ethylidene. Ethylidene chloride. Ethylidene chloride. Okay? This will be its name. This will be its common name. Remember this thing, ethylidene chloride. Ethylidene chloride. And similarly, how to name the vicinal halides, bacha? For the vicinal halides, again count the number of carbons. There are 2 carbons. So ethyl will come, obviously. Ethyl will come. And now how to name the vicinal halides? It is actually ethylene. Ethylene dichloride. This is how you name the common names. These are what? These are the common names of geminal dihalides. Also write di bacha here. Here also write dihalide because these are dihalides, right? So this is how you write common names of geminal dihalide and vicinal dihalide. Here I will use the suffix ethylidene and here I have used the suffix ethylene. Remember this thing, ethylene dichloride. Here it is ethylidene chloride. Okay, everything is clear to you guys? Bacha, I am going to teach each and everything. Now, this is the list again given in your NCERT. Okay, you should know the names of each and every compound. Okay, each and every compound is extremely important because remember this, bacha, that the paper directly comes from the NCERT. Whatever molecule is mentioned in your NCERT, whether it is in form of examples, in text questions, or the back exercises, the exact molecule, the exact question will be asked. They do not do any interference in that. So please remember all the common names and the IUPAC names of these following. What are my favorite names? I'm going to discuss those with you guys. Can you see that this halide over here, they have written bacha here that its common name is called vinyl chloride. I just taught you why. Why is it vinyl chloride? So because the chlorine atom here is attached directly to the sp2 hybridized carbon. Can you see this? This is called vinyl. And this one is called a allyl bromine. Why? Because the bromine atom or the halogen atom is attached to the sp3 hybridized carbon, which is right next to the sp2 hybridized carbon. Such kind of halides are called allyl halides. Okay? And my other favorite names are even this. Can you see the structure of this? Can anybody draw the structure of this? The structure of this will be this compound I'm drawing the structure of. The structure will look something like this. Here it is CH3. Here it will again be CH3. Here again it will be CH3. Okay, and here it will be CH2 and here it will be Br. So this is the structure of that is mentioned over here. And the name of this structure, can you see how many carbon atoms are there in the entire structure? It is 1, 2, 3, 4, 5. 5 carbon atoms. And whenever the 5 carbon atoms are attached in this manner, it means it is the isomer of pentane, right? So this isomer of pentane is called a neopentane. Okay? So here its common name will become neopentyl bromide. This is again one of my favorite molecules. My other favorite molecule is actually this structure. Can you see? CHBr3. So whenever you see any halogen written like this, for example, how do you write methane? Methane structure is CH4. Now what I'm doing, I'm replacing 3 of its hydrogen with some halogen atoms. Okay? So I am making through methane CHX3 kind of structure. So X can be, here X can be fluorine, bromine, chlorine, iodine, can be anything, right? So whenever I'm forming this kind of structure, then this kind of structure is called, bacha, what? Its common name is haloform. What it is called? Haloform. Haloform means what? Haloforms could be of anything. For example, here instead of X they have used bromine, so it is bromoform. If I would have used iodine here, it would be called iodoform, or chlorine, then chloroform, right? So this is how common names are given. And the IUPAC name, I think you have learned a lot in the 11th standard, so I'm not going to discuss them. But the common names here are important, so I discussed. Let's move forward. Let's move forward. Now we are here. Now we have, till now what we have completed, I told you, like what is a haloalkane, what is a haloarene, on what basis can we classify, on the basis of their hybridization we classify, then we read about the nomenclature. Now we're back. Now we come to the main point of this chapter, which is the nature of CX bond, right? So we are forming a bond in haloalkane. We're forming a bond between a carbon and a halogen atom. Everybody understands this, right? Halogen is bacha what? Halogen can be fluorine, chlorine, bromine, iodine. I'm telling this again and again. Okay? And what is the feature of these atoms, bacha? These are halogens. Halogens have how many electrons in their valence shell? They have total 7 electrons in their valence shell. Everybody knows this, right? This is a 9th class question. 7 electrons in their valence shell. Hence, these are electron rich. And also, bacha, halogens are what? Halogens are extremely electronegative molecules. Extremely electronegative atoms. Electronegative means what? They have the tendency to attract electrons towards themselves, right? Because they are electron deficient. Because as soon as they gain one more electron, they will become a stable structure, right? They will gain a noble gas configuration. So they are highly electronegative elements. So if I attach a halogen atom to a carbon atom, bacha, what actually happens? Because This is very, very electronegative. So it will pull some of the electrons towards itself, and hence it will gain a delta negative charge, and rendering, because electrons are moving towards the halogen atoms, hence the carbon gains a delta positive charge. Remember this. Hence the CX bond in total becomes a polar bond. Is this thing clear to everybody? This bond becomes a polar bond. Okay? Number first point is clear, that CX bond is polar. Next thing is, what if I try to vary the X? See, if I try to vary the X, their bond length will be affected. For example, the CF bond length is the lowest. Okay? Then it will be the CCl bond length. Then it will be the CCBr bond length. Then it will be the CI bond length. But this is the order of the bond length. Remember this thing. Bond length order means what? As the size of the halogen atoms keeps on increasing, the bond length will increase. Then what will be the order of the bond strength? Bond strength. Bond strength order, who can tell me? Who can tell me the bond strength order? If this is the bond length order, then what will be the bond strength order? Who can tell me? Who can tell me? Bond strength order will be the reverse, right? Because the longer bonds are easier to break, and the smaller bonds are so close to each other that they're so strong that they're very difficult to break. Hence, the bond strength order will be that the CF bond will be the most strongest bond. Then it will be the CCl bond. Then it will be the CBr bond. And then it will be the CI bond. Remember this thing, right? Now, the next thing that we're going to talk about is what? The next thing we're going to talk about is the dipole moment. The dipole moment. Okay? Now, what will be the order of the dipole moment? So many times this question comes. Dipole moment is represented by bacha mu. Remember this. It is represented by mu, and dipole moment depends on two factors. What are those two factors? These are charge into distance. Okay? Charge into distance. So your dipole moment depends on two factors, charge into distance. So now tell me, which one will have the highest dipole moment and which haloalkane will have the lowest dipole moment? So bacha, the dipole moment, the mu order trend follows this. CH3Cl will have the highest dipole moment, right? And then it will be the CH3F. Then it will be the CH3Br. Then it will be the CH3I. On what basis are you telling this, ma'am? But can you see, bacha, that fluorine is your most electronegative element, hence it will be the most charged. Okay? But, ma'am, why have you put fluorine on the second number and chlorine on the first number? Because, bacha, the dipole moment also depends on the distance. The methyl and fluorine distance is too less, and hence the dipole moment is actually lesser for CH3F and CH3Cl. Cl is also equally electronegative. It is also a very good electronegative element, and also it has a longer bond length because the chlorine molecule is bigger, right? So the dipole moment actually follows this order. Okay? Everybody understood this? Can we move on to the next thing? Yes, the size is small. Now I'm moving to the next thing, bacha, which is its physical properties. So what are the physical properties of your haloalkanes? These are colorless when pure. This is a screenshot again from your NCERT. Every line is important. And bromides and iodides, they develop color when exposed to light. Yaad rakho. Remember this thing. Next is, many volatile halogen compounds have sweet smell. Initial chlorides, bromides and chlorofluoromethanes are gases. Okay? Initial, it means smaller molecules like methane, ethane. Chlorides, bromides and chlorofluoromethanes are gas, whereas higher members are liquids and solids. Okay? Smaller members are gaseous, while the higher members are liquids and gases. These are important points about the physical properties. Next physical property is the boiling point. Boiling point order is asked so many times in your exam, so you should know about this point. So, bacha, boiling point depends on what factors you should know about that first. So, I am a molecule, for example. As soon as I become big and big and big, I try to attach myself with more and more carbon atoms, with more and more halogen atoms, what is happening to me? I'm becoming more and more big, right? If I'm becoming more and more big, what will happen? So in molecules, what is present, bacha? What kind of forces are present? In molecules, van der Waals forces are present. Van der Waals force. And van der Waals force is directly proportional to the molar mass. Remember this thing. So as the mass or as the number of carbon atoms, as the number of halogen atoms increases, van der Waals force will increase. Similarly, I just told you that the CX is a polar bond, right? Because it is a polar bond, therefore there will exist another kind of interaction in the haloalkanes molecule, which is dipole-dipole interaction. Dipole-dipole interaction. Remember this thing. On which two factors the boiling point depends for haloalkanes? Number first is van der Waals forces. Because as the size will increase, molar mass will increase, and hence the van der Waals force will also increase. And the next interaction that exists is the dipole-dipole interaction. And due to these two kind of forces, due to these two kind of interaction, what happens? That their boiling point, that the boiling point of haloalkanes is higher. Than what? Than your hydrocarbons. Remember this thing. Then your normal hydrocarbons, even if you are a hydrocarbon of similar molar mass. For example, I am a hydrocarbon of 180 mass and you are a haloalkane of 180 mass. Now, which one will have a higher boiling point? The haloalkane will have a higher boiling point because the haloalkane also contains the dipole-dipole interaction, and due to which its boiling point will increase. Hence, the boiling point is directly proportional to the molar mass of the molecule. Number first thing. And also number second is the dipole-dipole interaction between them. Okay? So as the mass of the haloalkane will increase, the boiling point will also increase. And similarly, the boiling point, bacha, is inversely proportional. Remember this thing. Inversely proportional to the branching. It means what? It means as the branching in the molecule keeps on increasing, the boiling point will decrease. Why? Because if the branching increases, what happens? The molecule gains a spherical shape, right? If I keep on increasing the branching, those kind of isomers become kind of spherical in shape, and hence their surface area reduces. Hence their van der Waals forces also reduces. Therefore, the boiling point also comes down. So boiling point depends on all these things. Okay? And now let's write the order, the trend for boiling point. The trend for boiling point will be, bacha, therefore, alkyl iodides will have the highest boiling point. Why? Because the iodides are the biggest molecule and also the heaviest molecule. Hence, they will have the most van der Waals forces. Then it will be the RBr molecule. Then it will be the RCl molecule. Then it will be the RF molecule. Everybody is understanding this? Everybody is understanding this? Okay? Now let's move forward. Okay? Let's move forward. Now, who can tell me the order of these boiling point? What will be the order of the boiling point? This is molecule A, this is molecule B, and this is molecule C. I am looking at the chart box. Please answer this question. Who can tell me the answer to this question? Who can tell me the answer to this question? Yes, Mathilesh. Yes, you are correct, Mathilesh. Who can tell me the answer? A, B, C. Among A, B and C, what will be the order of the boiling point? What will be the order of boiling point? I am looking at the chart box. Please answer me. Please answer me. The first correct answer is given by Subhlakshmi. The first correct answer is given by Subhlakshmi. Very good, very, very good. Then the next correct answer given by Muhunthan. Then the next correct. And all others are wrong till now. The MG also gave the right answer. Very, very good. Bacha, I just told you. As the branching increases, boiling point decreases, right? Boiling point is inversely proportional to branching. I just told you. Can you see that this is the most branched molecule? Hence, it will have the lowest boiling point, right? It will have the lowest boiling point. Then can you see among these two, this is the this Br, this is the this Br. Can you see this is again an isomer of this molecule? Hence, it will have even lower boiling point and then it will be the A. Okay? So this is the correct order of boiling point. That's why I've included this example, because you're going to have confusion between A and B, right? So this is the correct order for the boiling point series. Everybody understood this? Next, let's move on to the boiling point of haloarenes. Haloarenes. Who can tell me? So, bacha, can you see that what kind of isomer is this? When two chlorine atoms are attached right next to each other, such isomer is called a orthoisomer, right? This kind of isomer, when they're separated by just one carbon, is called a meta-isomer, right? And this is called a para-isomer. Everybody is very familiar with this terminology, right? Now you have to tell me the boiling point and the melting point or the order of these three. Ortho, meta, para. Between these things, number first that we're going to discuss is the boiling point, because I haven't taught you about melting point yet. So let me know what will be the order of the boiling point. Who can tell me? Who can tell me the boiling point order? The first answer that I'm getting is CAB. CAB. And the next is CBA. Okay, so you are telling me that C, para, will have the highest boiling point. You are absolutely wrong. Absolutely wrong answers are coming. Absolutely wrong answers are coming. Bacha, the boiling point in haloarenes, please correct this if you are wrong. The boiling point order is ortho will have the highest, then it will be the meta, and then it will be the para isomer. This is the order of the boiling point. This is the order of the boiling point. Remember this thing. Okay? Why? Because this is going to have most interactions. These are so close. These chlorine molecules are so close. And then these are going to have even lesser interactions, and para will have no interactions. Hence, the boiling point order follow this order. Now, the melting point order. What will be the melting point order between these? Extremely important question. Who can tell me the melting point order? Yes, it will be ortho, meta, para for the boiling point. What will be the melting point order? Somebody is saying CAB. CAB. Very good. Who told me that? Who told me? Amrita Varshini. Very good, Amrita. You are absolutely correct. So, bacha, melting point order here is para will have the highest, then it will be the ortho, then it will be the meta. Now, as I told you, that boiling point depends on what factors? Boiling point depends on the mass as well as the branching, how much the molecule is branched. That is the thing that the boiling point depends upon. Boiling point depends upon the van der Waals forces, that is it. But what does melting point depends upon? Melting point depends upon, bacha, the arrangement of the crystals, right? If the crystal arrangement is very symmetric, then that molecule will have a very high melting point. Now look at the para isomer. The para isomer here, when it's arranged in crystals, bacha, when it is arranged in crystals, what happens to it? The crystal is very symmetric. Hence, it has the very high melting point. This is true in every case. Whenever, no matter what molecule you're talking about, whenever you want to find out its melting point, the melting point always depends upon the symmetry of the crystal lattice that is formed, right? If the crystal lattice is very symmetrical, it will have the highest melting point. Hence, the melting point order is this, which I just told you, right? Now, let's move on to the next. The next is, bacha, the question, index question, extremely good questions. All the good questions I've included here. Whatever cannot be discussed as theory, I've included as questions over here. Arrange the set of compounds in order of increasing boiling points once again. This is a homework question for you guys, because I don't want to leave even one thing. So please note down that this is a homework question. Let me know in the chat box below if you know the answer to this question. This has two parts. Remember this, and I want answer to both the parts of the question. This is helpful for your chemistry exam. Extremely good questions. All the good questions are included here in these slides. Next physical property that we're going to talk about is density. Okay, so density, bacha, you just have to know one thing, that these are actually heavier than water. Bromo, iodo and polychloro derivatives of hydrocarbon are heavier than water. Okay, that is it. And density depends on what? If the number of carbon atoms increases, if the number of halogen atoms increases, the density will also increase. That is its simple basic funda that is given. Next is solubility. Again, interesting property. So what do you think? What do you think are haloalkanes soluble in water? What do you think? What do you think? Are haloalkanes soluble in water? So, bacha, haloalkanes are only very slightly soluble in water. Slightly soluble in water. Remember this thing. Even though I told you that the CX bond is actually a quite polar bond, but still only they are very, very slightly soluble in water because they have a very big methyl chain attached to them. Do you remember they have a methyl chain? And methyl is a non-polar part, and that non-polar part makes it extremely difficult to ionize in the water because this bond that is formed over here is actually a very, very covalent bond. Okay, so these are very slightly soluble in water, and there's a whole theory given in your textbook. So, bacha, because you are taking a very subjective exam, right? This is you're going to be asked questions to which you have to write subjective answers. So, I cannot tell you just how to solve objectives right now. So, you need to know the reasoning behind anything, because then only you can form the answers. For example, this question might come, why the haloalkanes are only slightly soluble in water. So, what is the answer to that why? The answer to that why is that when I try, okay, look at this diagram now. So, when I try to dissolve the HCl molecule or any halide molecule in water, what should happen? So, if I'm trying to dissolve it in water, some hydrogen bondings of water should break, right? Some hydrogen bondings of water should break, and the water should be able to form new bonds with the HCl molecule, right? This thing should happen. So, some bond breaking and some bond making happen whenever we're trying to make something soluble. So, what happens in this case? That there is so much energy required to break the hydrogen bonding, and while the new bonds that are formed only releases very, very less energy. So, can you see that there is an energy deficiency cost? Because you need lots of energy to break the hydrogen bond, but the new bonds that you're forming with your haloalkanes, those bonds are not releasing enough energy. Hence, what happens? That therefore, these molecules are not very soluble in water. Okay, it's clear? It's clear? Beta, what is not clear about this diagram? For example, this is the HCl molecule that I want to dissolve in water. Mostly it will not be HCl, it will be something RCl molecule. Just correct this. This something will be RCl molecule will be there, and you're trying to dissolve it in water. And less energy is released, not as strong as original hydrogen bonds in water, because hydrogen bonds has so much more energy, and the new bonds that are formed are not strong. Hence, this is only very slightly soluble in water. Okay, understood this point? Shall I move on to the next thing? The next thing is this. Okay, we have discussed the solubility. Next is the methods of preparation of alkyl halides. Number for separation is from your halogenation of alkanes. Very, very important reaction. Okay. So, how can you prepare haloalkanes from your alkanes, bacha? So, you just took a methane molecule, okay, and you try to react it with Cl2 in presence of light or very, very high temperature. What happens? You get a mixture of chlorinated products. Can you see that you got a monochlorinated product, dichlorinated product, trichloro product, and also tetrachloro product. So what is happening in this case? When you try to react your methane molecule with chlorine gas in presence of light, you are getting a mixture of chlorinated products. This is chloromethane that we want, but instead we are getting a mixture of products. Hence, this method is not useful because I'm not getting one single product, I'm getting a mixture of products, right? And bacha, this reaction actually goes through the free radical mechanism reaction. Remember this thing, this reaction happens through free radical mechanism. Hence, the order of stability. Hence, the general ease of substitution of various hydrogens follow this sequence, which is allylic A will give a more product, then tertiary, then secondary, then primary, then methane. What is meant by this? I'll just explain it to you. I will explain it to you just now. For example, preparation of alkyl halide from halogenation of alkanes. Can you see that this is a alkane taken over here, right? And I'm trying to react it with chlorine and UV light, and I'm getting a mixture of products just like this. Can you see that I got two kinds of products? This is a primary product and this is a secondary product, right? So I'm getting two kinds of products. Now your answer should be, ma'am, which would be a major product and which would be a minor product, right? You're getting two kinds of substituted haloalkanes. Can everybody see that? Okay, two kinds, primary and secondary. And how do you decide that? I am going to tell you. Okay, you get these kinds of products. So, bacha, this reaction is actually possible with bromine as well as with bromine, also with chlorine and bromine. But bacha, with iodine, if you try to perform the same reaction, if you try to react methane with iodine in presence of light, what happens? The reaction, a reversible reaction happens. A reversible reaction means because HI is formed. HI is formed, which is a very, very strong reducing agent. So what it does, what is the function of a reducing agent, bacha? Reducing agent's function is it gives away H+, right? It gives away hydrogen. So it again gives away hydrogen to the CH3I molecule, and what happens? It again gets converted into methane molecule, right? So you're not getting the desired product that you want because HI is a very, very good reducing agent. Hence, to remove this HI, what you need to do, you need to add in the reaction mixture HiO3 plus HI, that will oxidize the HI to I2, and hence this reaction can be taken forward. So if you want to perform this free radical mechanism, addition of chlorine to the alkane molecule, is everybody understanding this? Okay, alkane molecule, you need to add some kind of oxidizing agent. For example, HiO3 or HNO3 in order to oxidize this molecule. Okay? Everybody understood this? Now next is a question on your screen. Who can answer this? Who can answer this question? There is a toluene given to you and you try to react it with chlorine in presence of light and only one product is formed. What product will that be? Option number A, B, C or D? Who can tell me the answer? Who can tell me the answer? Who can tell me the answer? I am looking at the chat box. Please let me know the answer. Okay, Krishna is saying A, Ram A, C. So whoever has answered C, absolutely correct. Absolutely correct. I just told you. Did you see that the substitution, that the ease of substitution order is allylic is more than tertiary, more than secondary, more than primary, more than methyl, which means what? Whichever will be the more stable free radical will be the major product. So here, if I take this molecule, this was the molecule with me, right? This was the molecule with me. And if I make a free radical of here, can you see if I take a free radical over here, this is called the benzylic free radical, which is the most stable free radical. Hence, your chlorine will get attached to this free radical, and hence the correct answer is option number C, because the most stable product is formed. Most stable product is the allylic, benzylic or tertiary products. Remember this thing. Okay, this concept is clear to you guys. Now next, this is again an example from your NCERT. Identify all the possible monochlorostructural isomers expected to be formed on free radical monochlorination of this compound. So the compound given to you is CH, and here it is CH3, here it is CH3, here it is CH2, and here it is CH3. And they have asked you that you're trying to form a monochlorinated product. Then how many kinds of monochlorinated products can be formed out of this? Who can answer this question? Who can answer this question to me? So, bacha, here the monochlorinated products actually depends on the type of hydrogen atoms that are present. Can you count how many different kinds of chlorinated products can you form over here? Can you form over here? So I can attach CH यहाँ पे and then CH2Cl here, it can come here, it will be CH, here it will again be CH3. ठीक है? Here I can either, okay, I will explain it to you only here. I can attach a Cl over here. ठीक है? I can attach a Cl over here. I can attach a Cl over here and I can attach a Cl over here. Right? So because I'm going to attach it one by one, so the total monochlorinated products that I'm going to get out of this reaction are 4. 4 monochlorinated products you can get. I'm going to draw all the structures on the board clearly for you guys. Wait for 1 second. Number first monochlorinated product is, here it is CH2, here it will be Cl, here it will be CH, CH3, and here it will be CH2, CH3. This is the first monochlorinated product, right? The next can be CH3, CH, here it can be CH3, here it will be CH, here can be Cl, and here can be CH3. Next monochlorinated. Similarly, the another monochlorinated can be CH3, then here CH3, here can again come the Cl, here it can be CH2, here it can be CH3, and the last can be CH3, CH3, here it will be Cl, sorry, I have already written Cl, so I will not write Cl over here. Okay, we have already done this though. Okay, here it will be CH, here it will be CH2, here it will be CH2Cl. So these are the 4 kinds of monochlorinated products that you can get. Okay, the answer is not 12, but who is saying 12? Next, this is again a very good question, in-text question again. Write structures of different dihalogen derivatives of propane. Who can write the dihalogen derivatives of propane means what? This is the propane molecule, right? How many dihalogen derivatives? So always remember the dihalogen can be geminal, vicinal, or even can be far apart. So there are too many possibilities to form. So this is again a homework question for you guys. Extremely good question. I'm not going to answer each and every question here because we are going to move forward. The next question here given on your screen is, among the isomeric alkanes of molecular formula C5H12, identify the one that on photochemical chlorination. Again, we're talking about photochemical chlorination, which is what, bacha? Which is chlorine in presence of light, right? So they have given you a molecular formula of C5H12, which is a molecular formula of pentane. So pentane has how many isomers? Who can tell me how many isomers there are of pentane? How many? Yeah, correct. The answer was 4. So how many isomers are there of pentane? Okay. So among those isomers that you get of pentane, which isomer will have only a single monochloride? Which isomer has the possibility of having just a single monochloride? So I'm going to answer this question for you so that your brain opens up how to answer such kind of questions. Single monochloride means what? That there should be just one kind of possibility of chlorine substitution. That is possible only with neopentane, just like this. CH3, CH3, CH3 and CH3, right? So this is the only possibility for the first answer. If I try to react it with chlorine in presence of light, what will happen? The chlorine will get attached to either of the CH3s, right? It doesn't matter. It doesn't matter if the chlorine gets attached here, here, here or here, because all are similar hydrogens, similar carbons, hence there is possibility of just one single product, right? Number second, 3 isomeric monochlorides. Who can answer this? Which isomer of pentane will show 3 isomeric monochlorides? Who can answer this? Yes, New. Yes, Vineet, you're correct about it. Which isomer will show 3 isomeric monochlorides? Who can tell me this? Very easy once again. The isomer is, for example, I've written CH3, CH2, CH2, CH2 and CH3, right? Now they have said 3 isomeric monochlorides you want to get as a product. 3 isomeric is possible in what case? For example, if I attach a chlorine over here, right? So if I attach a chlorine over here or here, it's one and the same thing, right? So one is this possibility. What is the second possibility? The second possibility is I can attach chlorine over here. Okay, I will just change the pen color so that you guys can understand, right? The second possibility is I can attach a chlorine over here, or if I attach a chlorine over here, it's one and the same thing. So second isomer is this, and the third isomer will be that the chlorine gets attached in the middle. So there are 3 isomeric chlorides possible with just this molecule. Similarly, with which isomer 4 isomeric monochlorides are possible? This is again I'm giving you as homework. Let me know in the chat box, because if you don't solve questions on your own, you won't understand. You have to draw structures with pen in your notebook. Only then you will get organic chemistry, understand organic chemistry. You cannot just look at the molecules, look at your teacher drawing in front of you and get good in chemistry. You have to fill your notebooks in this case as well. Correct? 1,1-dimethyl propane, somebody is saying. You are right, Jose. Joses, you're right, you're right. Joses has already given the answer. Very, very good. Very, very good. Next is selectivity and reactivity. I just told you that when we're talking about monochlorination in presence of light, what actually happens? What actually is happening that either a primary halide can be formed or a secondary halide can be formed, right? So can you see whenever I'm trying to react chlorine, the secondary halide is actually formed in the maximum quantity. This is the major product formed over here. But look, as soon as I change the halide, now I'm taking the halide as fluorine in the presence of light. What happens to that? Can you see that the secondary halide is actually the minor product, but the primary halide is actually the major product? So what is happening in this case? So in this case, a very interesting phenomena is happening of selectivity and reactivity. What does that mean? So if I am one molecule and I am someone who just reacts with everybody, no matter what. For example, there is a talkative child in your class and he talks to everybody. So he is a very reactive child in your class, right? He is talking to everybody. Doesn't matter if he is a topper in class, if he is not a topper in class. Okay? So he is talking to everybody. So he is just reactive and not selective with his group of friends. While a selectivity means what? Somebody who is very selective with his group of friends, right? For example, very introvert people are very selective with whom they will talk to, with whom they will not talk to, right? So what is happening with fluorine in this case? Because fluorine is so reactive, hence the major product formed in this case is a primary product. Why? Because it is super reactive, hence is choose to form a primary as a major product because it is least hindered, right? Least hindered, right? Primary carbon is actually the least hindered carbon. There are no methyl groups there to just stop its reactivity. Hence, it reacts so fast that it forms primary as the major product. Everybody understood this? But chlorine is a selective individual. Chlorine does what? Chlorine forms a major secondary product as a major product. Everybody is understanding this? Yes, bacha, today we will finish the organic. Now the selectivity and reactivity with fluorine and bromine. Just look at this example. I've taken a tertiary molecule and I'm trying to react it with fluorine and bromine side by side. With fluorine, because it is highly reactive and not selective, so what happens? It actually forms the primary halide. Can everybody see? So here it proves that fluorine is highly reactive molecule. Correct? While bromine forms the tertiary bromide, very stable, right? Because tertiary free radicals are very, very stable. It forms a tertiary bromide, which is a stable molecule. Hence, we can say that bromine is a selective molecule. Correct? So, this distinction is not given in your NCERT, but can be asked. So I've included all the possible questions that can be asked from your NCERT. Next preparation of alkane is the reaction of alkane with SO2Cl2. Again, so what do? You take a alkane, try to react it with SO2Cl2 in presence of peroxide and light. What happens? You get a alkyl halide with SO2 gas and HCl gas. Very good method of preparation because all of these are gases and hence they just evaporate away and we get a pure product of alkyl halide. It happens in presence of peroxide and HNu. Remember these things. Okay? Again, you can react so many with SOCl2. You can even react your ROH. Your ROH. I'm talking about alcohols now. So from alcohols you can get alkyl halides. How will you get from alkyl halides from alcohol, bachcha? ठीक है बच्चा, from alcohol you are trying to make an alkyl halide. So if you try to react it with PCl3 or with PCl5, ठीक है, or with SOCl2, with all these things bachcha, you will get a alkyl halide product. Remember this thing, these reactions are again given in your NCERT. You can go and check it out on the 3rd page, all the reactions with alcohol and phosphites. And even another thing is bachcha, for red phosphorus, with red phosphorus as well, red phosphorus in HI, you again get a alkyl halide as a product. Everybody is understanding this? Now let's move on to the next thing. Preparation from hydrocarbons. Okay, right now we did preparation from your hydrocarbon, which was methane. With methane, we made through free radical mechanism, we chlorinated brominated methane in presence of light. Very important reaction. Now we are trying to make from alkene. Again, a very important reaction. You try to react alkene with bromine water. What? With bromine water in CCl4. So the bachcha, bromine water is actually brown in color. This is again called a bromine water test. Remember this thing. This test is called bromine water test. So what is happening? Now I'm trying to make alkyl halide from an alkene. So what do? I take bromine water and I try to react it with alkene. Okay, in presence of CCl4, which is the inert solvent, and I get a vicinal dihalide. Can everybody see what I'm getting? I'm getting a vicinal dihalide. Can you see? Br is getting attached on both these carbons, right? So what kind of reaction this is? This is a addition reaction. Addition reaction. Can everybody see what I'm doing? I'm only adding 2 bromine atoms to the alkene and forming a saturated compound, which is ethylene bromide, a vicinal dihalide. Similarly, with propylene, again, this addition happens. Is this thing clear to everybody? Is this thing clear to everybody? Right? But in your, again, NCERT, this thing is given. But what kind of addition is happening over here? What kind of addition is happening? Bachcha, the addition that happens with alkenes is a anti-addition. Anti-addition. Remember this thing. So they can ask you about the stereochemistry. So what is the anti-addition? For example, I'm adding 2 bromine molecules to this double bond. That is it, that I have to do 2 bromine molecules to this double bond. So what I'm doing actually? Yes, bachcha, bromination and bromine water is the same thing. Same thing. See, this is called the bromine water test. What is happening in bromine water test? I started with bromine. For example, I took a beaker filled with bromine, which is of brown color. Okay, bromine water is brown color. And now I did what? I added alkene to it. Alkene to that bromine water solution. After some time, I will notice that the solution actually becomes colorless in color. So this is a test for the alkene, right? If it is able to convert the brown color solution into a colorless solution, it definitely confirms that the compound that you added to bromine was a alkene. See, can you see a colorless solution is obtained after that? Okay, now the next is this addition that we're doing to the double bond is actually anti-addition. Anti-addition means what? Anti-addition means that the bromine molecule, one of the bromine molecule will attack from the front and the other bromine molecule will attack from the back always. always this kind of attack will happen. And hence, can you see the product is, one is a dash product and the other one is a wedge product that you get. This is an anti-addition product. And you can also make an enantiomer of this, where you can convert the upper one as a wedge product and the lower one as a dash product. Okay? Abhi bhi, is the voice too low? See, the mic is right in my face. Is it still too low, bacha? Beta, class gets over in another 2 hours. Okay? 1.5 hours. We have already completed 1 hour. Next thing that I'm going to tell you about from alkenes, preparation from hydrocarbons from alkenes. From alkenes, the another preparation that we're going to talk about is, I took an alkene and I tried to react with a HI. I'm trying to react it with HI, and what is happening? I'm getting two kinds of product, which is the addition of HI. So the hydrogen, this addition, bacha, actually happens through Markovnikov rule. Markovnikov rule. Okay? Which says what? Markovnikov rule. Which says that, bacha, your iodine will get attached over here and your hydrogen will get attached over here. Okay? Both of these things will get attached. This is again a kind of addition reaction. Remember this thing. So what I'm doing, I've taken an alkene and tried to react with HI, and then both the H and the I will get attached instead of the double bond, and we will get a major product with I in the middle. It happens according to the Markovnikov rule. What is the Markovnikov rule? That the I actually gets attached to the more substituted carbon. More substituted carbon, when the attachment, when the addition is happening, it is called a Markovnikov rule. Okay? Okay? And the order of reactivity for the halides, hydrogen halide, is HI is more reactive than HBr, then HCl, then HF. And why is that the case? Why is that the case? Because HI bond is a weak bond. Everybody remember, HI bond is very, very weak, so it is very easy to break. Why it is weak? Because iodine is a very big molecule, hydrogen is a very small, chotu sa molecule. Hence, the bond form between a big and a small molecule is always a very weak bond. And also because iodine is so big, the bond is so long, hence it is very easier to break. Therefore, the reactivity of HI will be more than HBr, then HCl, then HF. All these things are clear to everybody. All these things are clear to everybody. Okay? Next, you've done this, and from the alkenes, another peroxide effect. This is again not mentioned in your NCERT, but it is directly asked in the question. This kind of question is asked in examples and also in back exercises. So please understand, when you react alkene with HBr in presence of peroxide, what happens? See the simple reaction that I told you here, what was the major product? The major product was that the I was actually getting attached to the more substituted alkene, right? But if you choose peroxide with HBr, what will happen? Now the Br molecule gets attached to the lesser substituted alkene and the H will get attached over here. Hence, the product that you're getting over here is the anti-Markovnikov product. Anti-Markovnikov product. Remember this thing. The product that you're getting is a anti-Markovnikov product. Okay? And with no peroxide, you're getting this kind of product. So please remember this thing. Okay? Okay? Now next, allylic halogenation. So sometimes what happens, you can even get a allylic halogenated product. What is the allylic halogenation? When the halogen gets attached to the allylic carbon. What is the allylic carbon? This sp3 hybridized carbon. This sp3 hybridized carbon is the allylic carbon. Everybody is familiar with this, right? So this is the allylic carbon. Again here, this is the sp2 carbon, right? And the carbon right next to it is the sp3 carbon. So if the halogen gets attached to this sp3 carbon, we call it the allylic halogenation. And in what condition it happens? It happens when I take a chlorine and I try to heat it like 500 degrees Celsius and try to heat it. Then I get a allyl chloride, right? And here also I'm getting a allylic chloride. So whenever you take chlorine and heat it and heated in presence of alkene, and there is a possibility of an allylic product, then an allylic product will definitely form. Again, a very important reaction. Next reaction is the N-bromosuccinamide. Very important reagent, asked so many times in your exam. What is the structure of reagent? You must know that this is the structure of reagent. Please look at this structure. This is actually the structure of N-bromosuccinamide. Okay, what do? You again take a alkene and try to react NBS with it, and in presence of light and peroxide, the product that you get is actually a allyl bromide. Again, bromination happens here at the allylic. Can you identify the allylic carbon? The carbon right next to the sp2 hybridized carbon is the allylic. Hence, Br gets attached over here. So you get a allyl bromide over here. Okay? Who is asking propane formula? What class are you attending? What class are you attending? You don't know what's the formula for propane. Who is this individual? ठीक है बच्चा, you are preparing for class 12 board exam. You cannot ask me this silly question, ma'am, what is the formula for propene? Now next is बच्चा selective bromination of benzylic carbon that we're talking about. ठीक है, again, here I told you that there will be allylic substitution over here, okay, with the same reagent NBS. So with the same reagent NBS, now we're trying to do benzylic substitution. What will happen? I took a benzene and now the bromine gets attached to this benzylic carbon. What is benzylic carbon? Again, it is sp3 hybridized carbon attached right to the benzene ring. Okay? Here the bromine substitution happens. So these are few of the bromination reactions. Clear? Now next is a very important name reaction. Hunziker, please do not skip it. Hunziker name reaction, very important. This is again an exclusive method for the preparation of alkyl bromides. Remember this thing. Hunziker is used for the preparation of alkyl bromides where you take silver salt of fatty acid, carboxylic acid is taken. Okay, see, I took carboxylic acid, silver salt, and I tried to make this product, RCOO minus Ag plus, right? And then I try to react RCOOAg that I formed here with Br2 in presence of CaCl4. The product that I get is RBr. Can you see that I'm losing this COO molecule from here? This gets lost as CO2 and this forms AgBr as well, and the product that I'm getting is a alkyl bromide product. Again, in this case, what will happen? This COO will get lost as CO2 and here Br will get attached. So it's a process of bromination. In Hunziker, you do what, bacha? You take a carboxylic acid and you react it with silver hydroxide, right? And you make a silver salt of fatty acid. This is called silver salt. And then you react silver salt with bromine atom in presence of CCl4 and you get a alkyl bromide product. ठीक है? Now next is Finkelstein reaction. Again, very important name reaction. So many name reactions are here in this chapter. What is Finkelstein? This is again a preparatory method of haloalkane. What kind of haloalkane you're forming? You're forming a alkyl iodide. What you're forming? You're forming a alkyl iodide. Remember this thing, this is a preparatory reaction. So I just took a RX, okay, which is any alkyl halide you take. This is again a kind of halogen exchange reaction. Halogen exchange reaction. Remember these things. So what is happening? I already have a alkyl halide with me. But the alkyl halide that I have is either a chlorine or a bromine alkyl halide. Okay? And then I try to exchange this either chlorine or bromine with NaI and exchange this with iodine. Okay? And I get a alkyl iodide. So this particular reaction where you try to exchange halogens which are either chlorine or bromine with NaI iodine, the product you get is alkyl iodide and it has a specific name called Finkelstein reaction. It is again a halogen exchange. Very important name reaction. Everybody understood this? Everybody understood this? Beta Hunziker is in the NCRT. ठीक है? Next is Finkelstein mechanism. How does Finkelstein actually takes place? So, bacha, Finkelstein takes place through SN2 reaction. What is a SN2 reaction? Once again, I'm going to tell you. What is a SN2 reaction? Where, bacha, the attack happens from the back side. This is a, wherever you see a 2 number, now I'm going to tell you a very simple trick. A 2 number means it is a one-step reaction. One-step reaction. And in one-step reaction, what happens? The attack happens from the back side. Hence, if the configuration of the alkyl halide that you take, for example, this chloroalkene you took was in the S configuration, now after exchanging it with iodine, what will happen? You will get a R configuration. Here the chlorine was attached with dash lines. The iodine that you're going to attach will be with the wedge line. So this stereochemistry I'm going to teach you with all the reactions which are important. This is a SN2 reaction. You should know because SN1 and SN2 are in your syllabus. So Finkelstein is a SN2 mechanism where inversion of configuration happens, right? Inversion of configuration happens. Next, Finkelstein reaction mechanism. Again, important point that I'm going to teach you is which halogen will replace it. These things are a little higher category things that I'm teaching you about. Probably you do not need it for the board exam purposes, so I will skip it, but I've taught it in the name reaction series as well that I did it. If you want to learn more about the reaction mechanisms, we're going to do that. But the major important thing I've taught you that you should know Finkelstein is a SN2 reaction. That is the major important thing. The other things we're going to learn when we learn through the JE perspective. Okay, abhi right now you do not need these things, but this will be available in the PDF, so you can just go through them if you like. Next, another is a Schwarz, another name reaction, Schwarz reaction. This is again another kind of halogen exchange reaction. Okay? The last Finkelstein, what you were doing? You were exchanging the halogens with iodine. Here you are exchanging halogens with fluorine. You are developing an alkyl fluoride. Remember this thing. So this reaction happens with metal fluorides like AgF, Ag2F2, COF2 and SbF3. What happens? You take any alkyl halide, could be alkyl bromide, could be alkyl chloride, right? And could be alkyl iodide, and you replace it with AgF, and the product that you get is a CH3F product. This reaction again is a SN2 reaction mechanism, which means what? That the attack happens from the back, right? What is happening? This will leave and fluorine will attach over here, right? This will happen. So the attack is happening from the back. So this is a SN2 reaction. Remember this thing. Okay, the Br is leaving, the F is coming over here. It is a kind of substitution reaction. Okay, nucleophilic substitution reaction. This kind of reaction happens SN2. It means again here inversion of configuration will take place. Okay? Beta, you can form any fluorides, not necessarily fluoromethanes. You can form fluoroethanes, propanes, butanes, any. But it would be a fluoro-substituted compounds, right? Schwarz reaction is a fluorine exchange reaction. Everybody understood this? Okay? Next is preparation of haloalkanes. Next is from the alcohols. From the alcohols, how can you prepare the haloalkanes? So, for the alcohols, you took a HX, any acid, you can take HCl, HBr, HF, HI, and in presence of catalyst, and then you write RX. Then you are doing what? This OH is actually leaving, and you are substituting this with the RX. So, what is happening? OH leaves and is substituted by a halide. So, you get an alkyl halide in this case. The catalyst here can be a dehydrating agent such as ZnCl2 or concentrated H2SO4. What will be the reactivity order of the halides? The reactivity order of the halides will be HI will be more reactive than HBr and then HCl. Why? Again, because the reactivity means what? Because this bond, it should be easier to break this bond, right? And it is easier to break the HI bond because iodine is a very big molecule. Hence, the bond is longer, easier to break. And the reactivity order for the alcohol. For the alcohol, the reactivity order is the tertiary alcohols are most reactive, then secondary, and then primary. What does it mean? It means that the reaction takes place through carbocation mechanism, right? Whenever tertiary bachcha comes over here, tertiary, it means what? Tertiary alcohols means the most stable alcohol, and the most stability we see in which kind of reactions? We see in those reactions wherever carbocation is forming. Correct? Now next, another from alcohols again, and they have tried to replace this OH with HBr in presence of H2SO4, and you again get a bromomethane. Similarly, you can also perform this reaction with KBr molecule as well. Instead of HBr, KBr can also be used, right? Because it is again an ionic molecule, right? It will be K plus and Br minus, right? Now, so the mixture of KBr and H2SO4 is not used in case of secondary and tertiary alcohols, as the dehydration may occur and give alkenes. Again, an important point. What will happen that the KBr you cannot use in presence of secondary or tertiary alcohols. Otherwise, this substitution will not happen. This substitution is happening that the OH is going away and it is getting replaced by a Br molecule. But instead what will happen, an alkene will be formed. Okay? Now next with PX5 again, from alcohols you can again prepare alkyl halides with PX5 with SOCl2. This is a very good method of preparation, because all other things created here will be gaseous products, so you will get a very pure alkyl halide product. Okay? Next is from hydrocarbons. Once again, from hydrocarbons you're getting what? You're getting X2Fe. What you're doing, you took a toluene, okay, you took a toluene and tried to react it with X2 in the presence of a Lewis acid, okay, Fe and dark, and what you're getting a orthohalotoluene and parahalotoluene. Okay, this is a very important reaction of making haloarenes preparation. Okay, you cannot directly attach bromine to the benzene ring here. Instead, you use a Lewis acid like Fe or your FeCl3. Any Lewis acid you can use, and then the substitution happens at the ortho and the para position. Why? Because this CH3 is what kind of group? CH3 is ortho-para directing group, right? Because this is ortho-para directing group. Hence, the incoming nucleophile actually attacks the ortho and the para position. Okay? Namaste everybody. Ma'am would teach that. Okay? Next, amines. From amines, we are now talking about the preparation methods for haloarenes. From amines, again a very important name reaction is there, which is called the Sand-Mayo reaction. You will again read about it in amines chapter. So I just took this compound, which is amine compound, okay, and then I tried to react with NaNO2 plus HX, right? And then I formed benzene diazonium halide. What did I form? I formed a benzene diazonium halide in presence of NaNO2, HX, and a very cold conditions. So after forming the benzene diazonium chloride, I try to react it with Cu2X2. So whenever I do that, this entire reaction, this whole reaction, bacha, is called the Sand-Mayo reaction after the aryl halide is formed. Until the aryl halide is formed, this entire reaction is called the Sand-Mayo reaction. First you took the amine, then you formed a diazonium halide with it, and with that diazonium halide you reacted Cu2X2 and formed a aryl halide, right? And here the halogen can only be chlorine and bromine. Remember this thing, can only be chlorine and bromine, because with iodine, if you want to make a iodide product over here, right? If you want to make a iodoarene over here, you just need to react the diazonium salt with some Ki and mix the solution, and you will directly get the product. You do not need to use Cu2I2 over here. You just need to react it with Ki and you will get a iodobenzene. Is this thing clear to everybody? Is this thing clear to everybody? Beta, I will teach everything one by one. Please give me some time. Now next is the reactions of haloalkanes. Now we are here with the reactions of haloalkanes. Nucleophilic substitution reaction. So these haloalkanes show three kinds of reaction, which is nucleophilic substitution, elimination reaction, as well as reaction with metals, and we're going to study each of them and why do they show these reactions and what are these reactions. Okay, we are going to do them one by one. So bacha, in nucleophilic substitution I'm going to teach you one more thing. What is nucleophile? What is a nucleophile? So bacha, nucleophile is anything with a negative charge. Nucleophile is what? Which is electron rich, which has a negative charge, right? And what does your haloalkane look like? Your haloalkanes look like somewhat like this. The carbon has a delta positive charge, the halogen has a delta negative charge, right? Now what you're doing, you're trying to do nucleophilic substitution. Substitution means what? You are removing something and substituting your nucleophile in its place, right? Now, because this already has a negative charge, so it will attack something which is positive, which is the carbon, right? So the attack will happen like this, and this bond, the CX bond, will break in nucleophilic substitution reaction, and the nucleophile carbon bond, new bond will be formed. So this is how the reaction will be done in nucleophilic substitution reactions. Correct? And what can be the nucleophiles? I just told you the nucleophiles can be anything which has a lone pair of electrons or a negative charge. For example, if I use the reagent NaOH, so NaOH or KOH will give out the nucleophile OH negative, and hence the product will be ROH. I started with NeRX, remember this, and I'm replacing this X one by one with one nucleophile, with OH, with H2O. If I have H2 as a nucleophile, I will again get the product as ROH. If I have NaOR, then I will get the product as ROR. Okay? So that is ether. So these are all the nucleophiles that are there, the reagents, the nucleophiles, and what kind of substitution will happen. Substitution is nothing. You have alkyl halide, right? You just remove the halogen, and after removing, just replace the halogen with any of these nucleophiles, right? And the major important thing to notice is that the KCN, remember KCN and AgCN, look at these molecules. These both contain CN molecule, right? Both of them contain the CN molecule, but with the KCN molecule, the final product that you get is actually a RCN product whose name is a nitride, which are called nitrides. But with AgCN, you actually get a RNC product. Here the connectivity is through nitrogen atom, which is called isocyanide or a isonitrile compound. Remember this thing, that both the connectivities in both the cases are different. If I'm using the reagent KCN, then the connectivity will be through carbon. If I'm using the reagent AgCN, then the connectivity will be through the nitrogen. And why is that the case? Why is that the case? So, bacha, the CN molecule has a structure somewhat like this, right? ठीक है बच्चा, beta, I will teach you one by one everything. Beta, CN molecule is somewhat like this. This is again a very good theory question that can be asked in your exam. Ki why AgCN gives a isonitrile product and why KCN gives a normal nitrile product. So, bacha, this is the CN nucleophile, right? So, what can happen? This CN nucleophile is actually, so what happens? This has a lone pair of electrons on carbon as well, and this is a resonating structure of CN, just like this. This is a resonating structure of this kind of molecule as well. Remember this thing, this is a resonating structure of this kind of molecule. Now with KCN, what happens? It is a ionic compound. It means it breaks down into K plus and Cn minus ions, right? So the Cn minus is here free. So with KCN, what happens? The attack actually happens from the carbon molecule, and hence the RCN kind of product is formed. But with the AgCN molecule, AgCN, so bacha, with the AgCN, this bond is actually a covalent bond, right? Because it is a covalent bond, hence it is not will be easily broken. So what will happen? Instead, the nitrogen over here, because it contains lone pair of electrons, will now attack your halide, which is your R plus, and therefore the final product form will be the RNC product. Everybody understood this? Because AgCN is a covalent molecule. Hence, this bond will not break. This AgCN bond will not break. Instead, what will happen? The nitrogen will be more available to donate its electron pair to the alkyl atom, and hence this kind of addition will happen. This kind of addition will happen. Hanji, Hanji. Everybody understood this? This is very important thing. And similarly, you can see the same thing happens with KNO2 and AgNO2. With KNA2, the addition, the linkage is through the oxygen atom, while with AgNO2, again the linkage happens through the nitrogen atoms, and you get a nitroalkane. With KNO2, you get a alkyl nitrate. So these are some of the few important things that you should remember from this table. Let's move on to forward with the number first mechanism. Substitution reaction. I'm talking about substitution. Ma'am, what is the mechanism behind them? So, bacha, there are two kinds of substitution mechanism. I'm already telling you. Number first that we're going to discuss is the SN2 mechanism. So, what is a substitution reaction? That what happens? There is a nucleophile approaching. Nucleophile is anything with a negative charge or lone pair of electrons. Okay? And this is your haloalkane. So what will happen? Because it is a substitution, means something will substitute the other thing. So what happens? As in the SN2 mechanism, this negative charge start to approach this atom, this halal alkyd, and form a transition state over here. So the bacha transition state is something where, can you see, in the transition state the carbon atom is attached to 1, 2, 3, 4, 5. 5 atoms. So here the carbon atom has 5 bonds formed. Hence it is very, very unstable, right? Carbon can maximum form 4 bonds, but in the transition state of SN2 mechanism, the carbon atom has 5 bonds. Remember this thing. And also transition states are something which can never be isolated, which means I cannot look at the transition state at any point of time experimentally. They can never be isolated. They are only predicted, right? And the last step that happens is, now the OH attacks from the back side. What is happening? Back side attack is happening. Can you see that here the leaving group is on the right hand side, but the attacking group is coming from the left hand side. Hence this goes away and the inverted product is formed. Inverted product. Inversion of configuration happens in SN2 mechanism. Inversion means what? If I started with the R configuration, I will get a S configuration as the product, right? It means what? It means that if you get this thing should be clear, that enantiomeric products will be formed in the SN2 mechanism. Okay? Next thing. Yes, bacha, you should know about all the reagents. That is one thing. That is one given thing. Okay. Next, SN2 mechanism. Now we're going to look at the optical activity. So what happens? This is a nucleophile. Okay. So optical activity, I'm going to teach you which one will be more optically active. First, let us see this diagram. Then we will go back to that diagram. Okay. That was your NCERT diagram. Now, bacha, if the OH is attacking from the back side, what do you think? When the OH can have the best attack? When there are very, very less hindrance, right? If there are big methyl groups present over here, then it will cause too much hindrance. Hence, SN2 reaction cannot happen very, very nicely, right? So, therefore, I can write down the reactivity order of the alkyl halide for the SN2 mechanism, right? So, what will be the reactivity? What will be the reactivity order for the alkyl halide for the SN2 mechanism? Then, bacha, your methyl halide CH3X will be most reactive, and then it will be your primary halides, then it will be your secondary, and then it will be your tertiary. Remember this thing, because in tertiary what will happen? There will be too many methyl groups there, which will cause hindrance to the OH attacking from the back. Hence, the reactivity will come down. So, this is the reactivity order for the alkyl halide for SN2 mechanism. And for this alkyl halide, what should be the reactivity order for different halides? It is the same. It is R RI is more reactive than RBr, is more reactive than RCl, is more reactive than RF. Why is that the case? Because Ri bond, right? The carbon and iodine bond is easier to break because this is the longest bond, hence easier to break, and we want to break this bond, and as easily as it can be broken, it will be a faster reaction. So these are the reactivity orders that you have to follow. Okay, got it? Very, very, very good. Next, see, this is the same thing explained in this diagram. Can you see? In tertiary butyl, there are three alkyl groups attached over here, and the attack of the nucleophile cannot attack the carbon that is has to attack because it is now facing too much of steric hindrance, and secondary is facing a little lesser, primary is facing even much lesser, and methyl group is facing none of the steric hindrance because hydrogen atoms are really, really small. So we have discussed all of these things. Let me see if did I miss anything? Did I miss anything? I just need to see. But yes, I didn't miss anything. Let's move on to the next mechanism, which is SN1 mechanism. So what is SN1 mechanism? But I just took, for example, whenever SN1 is again the next thing. I didn't mention another thing in SN2 mechanism because you're taking a theory paper, then you should know SN2 few pointers that you need to write in your exam. Number first is inversion of configuration happens, है ना? Number second is, ma'am, there is a formation of a transition state. Number third is, ma'am, the attack happens from the back. These are the points that you should know. The next is what? The next is reactivity orders you can write of the alkyl halides. What should be the reactivity order, right? The next thing that you should write is that the SN2 reaction is actually only a one-step reaction. One-step reaction, right? It all happens in one step, right? The nucleophile comes from here and the leaving group leaves from here, right? It all happens in one single step. Okay, the next thing that you should know about SN2 reaction is, why is it called SN2? Because its reactivity depends on both alkyl halide as well as the nucleophile. Remember this thing, because its reactivity depends on both alkyl halide and nucleophile, hence it is called a SN2 mechanism. Remember this thing. Next thing, SN1 mechanism. SN1 again is a two-step mechanism. What happens? As there is a nucleophile and there is your alkyl halide. Now I want to do substitution of this alkyl halide. In step 1, what will happen? First of all, the leaving group will leave. After the bromine has left as Br minus, this carbon is left with a positive charge. Remember this thing. So here there is a formation of carbocation. Here is a formation of carbocation in SN1 mechanism, right? And now after the carbocation is formed, now the nucleophile will attack over here and get attached. Right? So this is how SN1 mechanism actually takes place. Is everything clear to everybody? These are the steps. This is a two-step mechanism. Carbocation formation happens. Hence, what will be the reactivity order of the alkyl halide now? What will be the reactivity order of the alkyl halide now? I haven't left any space to tell you the reactivity order, so I will write it over here. The reactivity order of alkyl halide. Alkyl halide will be what? Now, the tertiary alkyl halides will be more stable, more reactive than secondary, then your primary, and then will be your methyl alkyl halide. Why is that the case? Because tertiary carbocations are more stable, hence this will be the reactivity order for SN1 mechanism, which is a two-step mechanism, right? And the order for the halides is simply the same, which is Ri is again more reactive than RBr, then RCl, and then RF. Why is that the case, bacha? Because Ri bond length is again very, very easier to break. Why is it called SN1 mechanism? Why is it called SN1 mechanism? Because its reactivity depends only on bacha what? only on alkyl halide. Remember this thing. It doesn't depend upon the nucleophile, just like the previous case. Here it only depends on one thing, which is the alkyl halide. So if the tertiary alkyl halide that is formed, it depends only on that. It doesn't matter on the concentration. Whatever can be the concentration of your nucleophile, it doesn't depend on that. Okay, everybody understood SN1 mechanism? Okay, now tell me, everybody understood this? Now I've made few molecules over here. Few molecules are made over here, right? Now first let us see this one, which is a benzene ring. Now the question is, will this benzyl, can you see that this is a benzyl carbocation? Can everybody see this? This is a benzyl carbocation. So will the benzyl carbocation show SN1 mechanism? Will the benzyl carbocation show SN1 mechanism? The answer is no. And will the this will show that this is forming a very stable carbocation, hence it will show SN1 mechanism, yes. And this will also show a SN1 mechanism, yes, because it is forming a what? A resonance stabilized carbocation. What is this? This is bacha resonance stabilized. I can make a resonating structure of this as well, allylic carbon. What will happen here? It will be CH2. Here it will be C double bond CH2. Okay, here, and this positive will come over here, right? So again I can make a resonating structure of here. Again similarly I can make resonating structures for this as well. For this as well. What can be the resonating structures here? For example, if I move the pi bond over here, the resonating structure will look somewhat like this. Here it will get the double bond CH2. The positive charge will move over here. This will get a double bond. This will get a double. Again, this can move over here, right? This can move over here, and again the pi bond move, and so does the positive charge. Now the positive charge comes over here. The pi bond comes over here. Here is the CH2 and here is this. So you can form lot many resonating structures. Again this pi bond moves over here, right? And the positive charge will move over here. So you can form too many resonating structures out of this. Therefore, these allylic and benzylic carbocations form very stable SN1 mechanism, very stable products through SN1 mechanism. ठीक है? Yes, and you are right that in SN1 mechanism, I'm going to tell you another thing. Somebody has mentioned that only polar protic solvents are used. Polar protic solvents are used in SN1 mechanism. Very, very important input from Vineet. Okay? But polar protic means what? Polar protic means whichever can easily give the H plus ions are called the polar protic solvents, right? And can you see that even a carbocation is formed in SN1 mechanism. Hence, due to carbocation formation, polar protic solvents are preferred. ठीक है? Next, optical activity. Again, because it's a theory paper, then definitions can be asked and will be asked. Then you can be asked to write a paragraph on optical activity shown by SN1 and SN2 mechanism. ठीक है? So, bacha, what is optical activity in general? If a paragraph comes for you to write, what will be the approach for you guys? So, bacha, optical activity is anything. Beta, which positive charge will matter? I could not understand your question. Please let me know what positive charge are we talking about. Optical activity, bacha, is that kind of activity. For example, I have a compound with me, right? And what I do, I pass a plain polarized light through it, right? And if that plain polarized light that I passed through the compound rotates, right? It can either rotate right direction or in left direction. If it rotates, then that tells us that our compound is an optically active compound. That is number one thing. ठीक है? अब optical activity, this everybody should know that PPL light rotation can only tell us the optical activity. We cannot look at the compound and tell कि, oh, this is optically active. No. only and only experimentally optical activity is determined. Only after you pass that light through it and it rotates, then only optical activity can be determined. Now, bacha, the other thing is the optical activity of SN1 and SN2 that we're going to read about now. So I just told you that SN2, in SN2 what happened? Inversion of configuration happens, right? Inversion of configuration means that if your compound was R compound, it could become a S compound. Okay? But in your SN1 bacha, what happens? In SN1 bacha, your enantiomers are formed. Enantiomers are formed. Okay? So this is the kind of optical activity that we're going to discuss about. What are enantiomers and what is a racemic mixture? All these things are formed in SN1 mechanism. What are they? What are their definition? One by one, I'm going to tell you. Okay? For example, look at this compound. Understand this one by one. Look at this compound. Can you see this carbon? This carbon is attached to 4 different groups. Hydrogen, iodine, chlorine, bromine. Right? So number first criteria for showing optical activity is that the carbon should be tetrahedral. Number first is the carbon should be tetrahedral, means it should be sp3 hybridized. Number first. And number second is that the carbon atom should contain all different groups. All 4 different groups, different atoms should be attached to the carbon atom. Okay? All 4 different atoms should be attached to the carbon atom. Everybody is understanding this? Only and only then it can show optical activity. Number third thing, for a molecule to show optical activity is the molecule should have absolutely no symmetry. There should be no symmetry. Remember this thing. There should be no symmetry. Symmetry should be absent. These are the 3 conditions for anything to show a optical activity. Only and only then your compound will be optically active. Okay? So any carbon which is first of all sp3 hybridized, second of all the 4 atoms attached to it are different and it contains no symmetry, then that carbon bacha is a chiral carbon. That carbon is called chiral carbon. That carbon center is called a stereo center. Okay, stereo center and chiral carbon are the same thing. Stereo center actually is that carbon through which you rotate the when you do the RS configurations, right? If you know about the RS configurations, then only you can you know what a stereo center is. And asymmetry, I told you that the molecule should contain absolutely no symmetry. So these are the conditions for chirality. These are the conditions for stereo center, and for the asymmetry is one of the conditions. Now what I've done, I've taken this optically active molecule. Now I know that this carbon is optically active because all the 4 groups are different. sp3 hybridized, there is no symmetry. Now I put a mirror in front of it. And the mirror image that I get, bacha, what will be the mirror image? For example, the carbon will be here. Bromine is above. Bromine above will be here. Chlorine is here. The chlorine will be visible over here. Iodine is going back. Iodine will be going back. Hydrogen going back. Hydrogen will be going back even in its mirror image. Right? Now, bacha, both the mirror images that we have gotten, if though both of these mirror images are non-superimposable, how they are? They are non-superimposable. Remember this thing. If the mirror images are non-superimposable on each other, then your compound is optically active. Remember these things. After satisfying all these conditions, these are the conditions can also be for a chirality, for a stereo center. And also after you put the mirror in front of them and both the mirror images are not superimposable, which means what? That for example, you took this molecule and I tried to put B molecule on A molecule. Will I get a entirely superimposed molecule? No, I will never ever get, no matter how much I try to rotate it, I will never ever get a superimposed molecule. Hence, this compound is optically active. These are the conditions for optical activity. The images should be non-superimposable on each other. Okay? Next is enantiomers. What are enantiomers? Bacha, I just told you, both the mirror images that we formed, both the mirror images are called enantiomers of each other. What are they called? They are called enantiomers of each other. What is their property? That both of them have the same molecular formula. They have the same connectivity, but their arrangement in the 3D space is different. That is their only difference in them, in the enantiomers. So look at the definition. Enantiomers have the identical physical properties, namely melting point, boiling point, refractive index, etc. all same. They only differ with respect to the rotation of the PPL light that I just told about. Plane polarized light. Only that one of the enantiomers will rotate in the positive direction or the right direction. The other will rotate in the negative or the left direction. So this is what an enantiomer is. Okay? Now, bacha, the enantiomers that can be formed can be of this. For example, this enantiomer is 70% found and this enantiomer is only 30% found. Okay? So these are separately just enantiomers. But what if both the enantiomers that I'm getting are actually 50-50%, are actually 50:50%? Then in such a situation where enantiomers formed are each in equal quantity, 50% of this, 50% of this, which means what? 50% rotate the light in the right direction, 50% rotate in left direction. Then a bacha, what happens? That compound is called a racemic mixture. That compound is called a racemic mixture, and this process of converting enantiomers into a racemic mixture is called racemization. Remember this thing. Okay? And now what is the optical activity of racemic mixture? So because a racemic mixture contains both kind of enantiomers, and that too 50-50. One is rotating the light in right direction, one in the left direction, and both in equal quantities. Hence, the racemic mixture is actually optically inactive. Remember this thing. Why? Because both the enantiomers have cancelled out each other, right? Both of their optical activities have cancelled out each other because they're both present in equal quantities. Hence, a racemic mixture is optically inactive mixture. Remember this thing. Okay? Next is identify the chiral molecule in this. Who can answer this question for me? Identify the chiral molecule. In first and between the first and second, which one is a chiral molecule? I'm looking at the chat box. Please answer to my question. And how is the preparation going on? How is your preparation for chemistry going on? Are you able to revise things with me right now? Yes, bacha, dextro and levo. Basically, dextro and levo. Correct. First, Rudra is saying first. Very good, Rudra. Rudra has been a very consistent student. The correct answer is first. That is true because this compound, even though this carbon has a little bit of symmetry also, and also can you see both of these attachments are same. Hence, this is not optically active and this is a chiral molecule. Correct, because this is the chiral carbon over here. Now, in this case, which is the chiral carbon? The second one is an easy part. Is it first or second? Again, somebody is saying first. So many answers. Correct. This is the chiral carbon. This one is again not carbon because this carbon has what? Two similar hydrogens are present. Two similar hydrogens and one CH2 molecule and one Br. Hence, this is not a chiral molecule. Only first one is. Correct. Chiral molecules. Now, the next property is retention. I just told you what retention is what. For example, I started with this molecule. Can you see? The OH is present here on the right hand side and I am trying to do a substitution reaction with HCl. And the Cl also got attached to the right hand side. Can everybody see that? Now, can you see? Now, the Cl attached to the same side where the OH was already present. Hence, what is happening to the configuration? The configuration is remaining same. Hence, such kind, if during a reaction no bond to the stereocenter is broken, the product will have the same general configuration of groups around the stereocenter as that of the reactant. So on which place OH was present, the Cl has taken the same position. Hence, this kind of optical activity is called retention. Retention. Can you see that no, this bond was not broken? The stereo center. What is the stereo center? This is the stereo center. No stereo center is broken. Stereo center bond is broken in retention of configuration. Okay. Now the optical activity is described for your SN1 mechanism. Can you see? Can you see, bacha? This is your compound. This is your compound. Okay. Here some X leaving group is here. So I want to make it leave and replace it with Y. What are the two possibilities that I have? The two possibility is either the Y can get attached on the same position as previously. Hence this product A is called retention of configuration, right? And this Y, otherwise this Y, if the X was here, the Y actually attacks on the back side and causes an inversion of configuration, right? So two kinds of possibilities are possible, right? And in SN1, both of these possibilities happen. That means the react happens from both the side, that is from the front as well as the back. Hence, inversion plus retention, both kinds of products are formed in your SN1 activity. That is, A plus B products are formed in your SN1, while only and only inverted products are formed in SN2. Okay? And if the inverted and the retended product, for example, both the enantiomers, see, these are enantiomers, right? And if both the enantiomers, A and B are what? A and B are enantiomers, right? And if both the enantiomers are, bacha, what? If both the enantiomers are 50-50 in quantity, 50% of this, 50% of that, then they will form a racemic mixture which will be again optically inactive. Optically inactive. Okay? Racemic mixture will be optically inactive, but the inverted and the retented product will be optically active. Okay? This racemic, only and only racemic mixture will be optically inactive. Racemic mixture is formed when the enantiomers are 50-50 in quantity. Okay? I've already discussed with you the SN1 mechanism, that the attack of the OH minus actually happens on both the sides. Can you see it is also attacking from the back as well as the front? From the back as well as the front, and two kinds of products are obtained in SN1 mechanism. So in SN1, enantiomers are formed. What will be your answer? In SN1, either a racemic mixture is formed or an enantiomer, or a pair of enantiomers are formed through SN1 mechanism, because inversion and retention, both kind of configurations take place in SN1 reaction. Is everybody able to understand that? Is everybody able to understand? Let me know. Next kind of reaction is elimination reaction. The next reactions we're going to talk about is elimination reaction. Yes, SN2 full inversion. So elimination, as the name suggests, we are eliminating something. What I'm trying to eliminate here? I'm trying to eliminate two things, which is your hydrogen as well as your halogen. Okay? And where is the hydrogen eliminating from? From the beta carbon. What is beta carbon? For example, this is my halogen compound. Here I have attached some halogen, right? And I want to eliminate this. Now what kind of elimination will happen? So the carbon, to the carbon to which the halogen is directly attached is called the alpha carbon, and the carbon right next to it is called the beta carbon, right? So from here the X will go away, and from the beta carbon the hydrogen will go away. And see, can you see that the what kind of elimination is happening? If the X is going away from the below direction, the H is going away from the upward direction. Can you see that? Yes, and an alkene is formed. So two atoms leave in elimination reaction, one hydrogen and one is your X. Okay? And it happens in the presence of a base, a strong base, for example KOH, right? So what I did, I took 2-bromopentane for example, and I tried to react it with a strong base KOH. What is the property of a strong base? So KOH actually gives away OH negative ion, right? So OH negative is a very strong base, and the property of a base is that it's a very good proton abstractor. Remember this thing. A base is a very, very good H plus abstractor. Remember this thing. It is a very, very good H plus abstractor. It will abstract the H ion, right, and it will form an alkene. Now there is a possibility of two kinds of alkene. Now the hydrogen can either be lost from this side, right, or the hydrogen can either be lost from this side, right. Both are the possibilities, because the hydrogen right next to the bromine will be the beta. This is also the beta carbon. This is also the beta carbon, right? Now from where the hydrogen will be lost? So can you see that this product is formed only 19%, while this product where the alkene is in the middle somewhere. Middle means it is more substituted. It is surrounded by more substitutions. So this kind of elimination is preferred more, which is 80% of the product is this. Which means what? That this kind of elimination is done through one rule, which is called 𝐳𝐸𝐵 rule. 𝐳𝐸𝐵 rule. What is 𝐳𝐸𝐵 rule says? When the elimination happens in such a manner that the major substituted alkene, that the majority product of the alkene is that which is most substituted. Remember this thing. Most substituted alkene is formed. Can you see? More substituted alkene is the stable product, while this is the minor product. Everybody understood this? ठीक है? ठीक है? This is called 𝐳𝐸𝐵 rule. So you must not get confused between Markovnikov and 𝐳𝐸𝐵. 𝐳𝐸𝐵 rule is used for the elimination reaction. So whenever we're forming alkene, what kind of alkene is formed? The more substituted alkene is the more better alkene, right? But what is the Markovnikov rule, bacha? What is the Markovnikov rule? Markovnikov rule, we talk about addition of something, right? Whenever we are adding something, if we are adding at the more substituted places, for example, OH, X, whatever, whenever we are adding something, we use the Markovnikov rule. When we are eliminating something, we use the 𝐳𝐸𝐵 rule, correct? Now the elimination versus substitution. But there is a competition between these two things. Because can you see, ma'am, nobody asked me this question. Ma'am, with OH minus, why are you forming an alkene over here? Because in the previous examples, can you see, in the previous example also I was using OH, and what I was doing? I was doing a substitution reaction, right? I removed this bromine and instead I attached the OH over here. I was using here OH as a nucleophile, right? But ma'am, here you're using the OH as a base, which is abstracting proton. Why such things that you're doing, ma'am? Like when to decide the elimination will happen, when to decide when the substitution will happen, when will it act as a substitution, when it will act as a elimination type of reaction. So, bacha, it depends on too many factors. For example, the nucleophile. The nucleophile here, which I am talking about, which has a negative charge. For example, the nucleophile we used here was OH negative, right? So, bacha, if the nucleophile is bulky means what? For example, look at this nucleophile, which is a tertiary butyl nucleophile, tertiary butoxide. This is tertiary butoxide. Can you see there are so many methyl groups attached over here? So it is a bulky nucleophile, right? So with the bulky nucleophile, what happens? An alkene is created. With the bulky nucleophile, elimination reaction happens, which means the bromine will also go and the hydrogen will also go and a alkene will be formed, right? But in substitution, but with a normal base, with a smaller base, this is a very, very big base, right? Bulky base. But with a normal base, for example, ethane oxide, what is happening? Substitution reaction is happening. The Br will leave and instead OCH2CH3 will now again act as a nucleophile, right? So first of all, the first deciding criteria is the nucleophile. If it is bulky, elimination reaction. If it is not bulky, substitution reaction. Number second is the primary alkyl halide. If you have primary alkyl halide, then what kind of reaction will happen? With primary alkyl halide, it will always be what kind of reactions? Who can tell me? Who can tell me? With primary alkyl halide, with secondary alkyl halide, with tertiary alkyl. So with primary, it will always be SN2 reaction. I just discussed with you guys. right? Primary means what? Primary has no bulky groups behind it, alkyl halide. Hence, the OH negative can directly attack over there, right? Because it has zero bulky groups, there is no steric hindrance. Hence, a normal substitution reaction from the backside will happen through SN2 reaction. So, with primary alkyl halide, you always have to use no brain of yours, just two SN2 substitution reactions. With secondary alkyl halide, there are two possibilities, right? It can either be a SN2 reaction, okay, or it can either be a elimination reaction, depending again upon so many factors like the nucleophile. Okay, if the nucleophile is bulky, it will be elimination. If the nucleophile is not bulky, it will be SN2. With tertiary, it will be SN1 reaction, or again elimination reaction. Elimination will happen when the nucleophile is bulky, elimination reaction. When it is not bulky, then substitution reaction, that through SN1 mechanism, SN2 mechanism. Everybody understood this part? Everybody understood this part? Yes, primary carbocation is unstable. Correct, correct, correct. Now reaction with metals, again very, very important reaction, which is the Grignard reagent reaction. Okay, with Grignard reagent, what are we doing, bacha? What are we doing with Grignard reagent? I just took a alkyl halide with magnesium and dry ether, and I made alkyl magnesium halide with it. Okay, what I am doing with Grignard reagent, I am taking a alkyl halide, I am trying to react it with magnesium and dry ether, and I am getting a alkyl magnesium halide, right? Again, here it is CH3Br, I am reacting with magnesium and dry ether, I am getting a Grignard reagent again. So, bacha, what is the bonding in Grignard reagent? Can you see it looks like this? There is a RMg plus and X minus kind of bond, right? So, what is this RMg bond? Can you see the bond formed between the carbon and the magnesium atom? This is a organometallic bond. What kind of bond it is? There is a metal and an organic compound carbon, so it is the organometallic compound. This bond is, bacha, a polar bond. Why? Because magnesium is a highly electropositive metal, hence it causes some polarity in the bond. This is a polar and covalent bond. Remember this thing. This bond is extremely covalent bond. Polar covalent bond is formed in the Grignard reagent. What you do? You take a alkyl halide, react it with magnesium in dry ether and form alkyl magnesium halide. ठीक है? Now next, Grignard reagent. What do you do? After you have prepared the Grignard reagent, what is the next thing that you do? You try to react. The Grignard reagent is extremely reactive things. Now you try to react the Grignard reagent with acid, alcohols, amines, acetylenes, H2O, or any acid. Basically anything which can give away hydrogen easily. You know that carboxylic acid give away hydrogen easily, and even your alcohols give away hydrogens easily. Your amines can give away hydrogens, your acetylenes, your H2 or any acid that can give away hydrogen, and you will be left with the alkane. So it acts as a very, very good hydrogenation reactions with RMGX. If you react with any compound, that easily gives away H plus, and in presence of RMGX, these compounds easily give away H plus. This can also be said about that. In presence of RMGX, which is a highly reactive compound, if you ever see a Grignard reagent and you react with any of these compounds, what you will get? You will get a simple alkane. That is it, simple alkane as a product. Now the next named reaction is a Woods reaction. What happens in Woods reaction? You just took a alkyl halide and you try to react it with sodium. Okay, in sodium metal in presence of dry ether. It is a name reaction once again of alkyl halide, and what happens? The alkyl halide, two alkyl halides will just form together. Okay, I will again form another alkyl halide over here. These alkyl halides will form a bond and the X will eliminate out, and you will be left with a ethane molecule like this. Okay, so you will get a joined product like this, a addition product like this, and the halogen atoms get removed. So a reaction just like this happens in woods. What is the mechanism behind this reaction? The mechanism is actually two kinds of mechanisms are reported, but nobody knows which is the correct mechanism. Hence, it is not given in your NCERT. Hence, we will not discuss it. Those mechanisms are not important. Now, reactions with haloarenes. Next reactions we are here now. We are here with the next kind of reactions, which are reactions of haloarenes bacha. So with haloalkanes, we studied SN1, SN2, elimination reactions, and your reaction with metals. Everybody is familiar with that. Now do you remember what happened in SN1? What happened in SN2? What happened with elimination? I know it's a lot to take in just one day. Organic is not something that you can just do in one day and nail it. If you are someone who is just studying it for the first time, it's going to be a really so much more things to just take in right now. I know that I'm just speaking it like you all know everything, but I know at this point there might be still some students who do not know anything that I'm talking about, and that, ma'am, I'm not able to understand that why you moving so fastly. Understand and please know that I am moving actually really slowly right now. Okay? This is the slowest I can go as a revision course. This is meant for revision because your exam is just after 2 days, right? You just have one more day and then is your exam. So I know all these things can be a lot to take in. Take this as a revision course, right? If you already know, if you have some idea of some of the things and you're struggling with some concepts, then this lecture is very helpful. Okay, you can learn new concepts even with today's lecture. There's no two doubts about it. But it will be very hard to retain those concepts in your head. है ना? That retention power comes with practice. है ना? With practice over and over and over. So I will not give you any false promises that after you see this lecture, you're going to score 95 plus. Only in one condition, that you already know these chapters and you've done a few of those chapters, and after this session is over, you still have the willpower ki ma'am, you just taught this chapter right now. I will again do all the questions, the NCERT exercises, the back exercises, the index exercises. Then that's for sure that you're going to score great marks in exam. But right now, I know it's going to be a lot to take in because I'm just saying a lot of stuff right now, right? If you have any doubts, please let me know. Now, nucleophilic, now I just told you, let's go back to the academics. In the haloalkanes, what did I teach you? I teach you that they undergo substitution, reaction, elimination, and reaction with metals, right? So, but in haloarenes, now we are in haloarenes. So, do haloarenes show nucleophilic substitution reactions? Let us check out. So, can you see a haloarene is where when up to a benzene ring, a halogen atom is directly attached to it, right? This is a haloarene. Now we know that the halogen atom is very rich in electrons, and what will happen? The electrons will now rotate inside the ring. This is called what? This is called resonance, right? Resonance structure. So due to the resonance, what will happen? Can you see so many resonating structures are possible of this chlorobenzene right now here? Hannah, so can you see that this bond, for the substitution reactions to happen, what was happening? This was your Rx and I was trying to substitute it with some nucleophile, right? So when the nucleophile was attacking the R or the carbon group, this X, Rx bond was cleaving, right? This I had to break this Rx bond. Only then a new R nucleophile compound was formed. Only then a new substituted compound was formed, right? This was the reaction of your haloalkanes. Okay? So can you see that I had to break a bond? I had to break the CX bond. But here can you see in the case of haloarenes, this CX bond, this CX bond is actually getting a double bond character. Double bond. Can you see? This is getting a double bond character. Hence, double bonds are what? Much more difficult to break. Right? These double bonds are so much more difficult to break. Hence, they cannot be broken. So, it is very difficult for them to undergo nucleophilic substitution reactions. Right? Number first reason that haloarenes do not show substitution reactions, nucleophilic substitution reactions. Why haloarenes do not show nucleophilic substitution reaction? Number one reason, Draw these resonating structure and show to the teacher, okay, ma'am, can you see that here this bond, CX bond, is getting a double bond character. So double bonds are difficult to break, hence they cannot be broken, hence nucleophilic substitution reactions cannot take place. Second reason, what is the second reason? Can you see that the carbon to which the chlorine is attached, this carbon is actually sp2 hybridized, right? Because this is a benzene ring carbon. So sp2 hybridized means what? The sp2 hybridized means that here this carbon is more electronegative carbon, right? Because here the S character is actually increasing, right? In sp2 the S character increases and hence the electronegativity of the carbon increases. These are the things you learn in your basic GOC. I've taught you that as well on this channel, right? So the electronegativity is actually increasing in this case. So more electronegative carbon will actually hold this chlorine more closely towards itself. Remember this thing. So this bond will again become more stronger bond, which will be difficult to break. Okay, second reason. Third reason is what? Third reason is that if I'm doing substitution reactions, then if I'm doing SN1 reaction, what was the criteria for SN1 reaction? That there should be formation of carbocation. If I try to form a phenyl carbocation, what is this? This is a phenyl carbocation. Phenyl carbocation, bacha, is very unstable. It is very unstable. Hence, they can never ever show SN1 reactions. Hence, again, they do not form nucleophilic substitution reaction for this reason, because phenyl carbocation is extremely unstable. Fourth and last reason is there is a benzene ring present. Can you see? Benzene ring is filled with what? Benzene ring has too many pi electrons, right? And pi electrons are what? Electrons, electron rich. Now, if you try to attack some nucleophile, which is again an electron rich nucleophile, right? Okay? Which is again a electron rich nucleophile. If you try to react it on the benzene ring right now, this electron will repel the electron of the benzene ring, right? I am a benzene ring. I'm already very electron rich. And now you're trying to attack a nucleophile on me, which is again containing too many electrons. So there will be repulsion, right? So due to this repulsion, again the benzene ring will cause repulsion, because benzene ring is already electron rich due to all the pi bonds. You cannot attack another negative charge on it because they will repel each other. These are the 4 reasons that you need to mention why haloarenes do not show nucleophilic substitution reactions. Is this clear to you guys? Next is, I explained this to you, the nucleophilic substitution reaction. But sometimes, bacha, nucleophilic substitution reactions do happen in drastic condition. Can you see that this Cl is getting replaced by OH? So nucleophilic substitution reaction has happened. But can you see the conditions that we're giving? We're giving it 623 kelvins of temperature and 300 atmosphere with NaOH and H plus. In those conditions only nucleophilic substitution happens. Another reaction. Another kind, if you want to increase the reactivity of nucleophilic substitution reactions, what another thing that you can do? As I already told you that the benzene ring is what? The benzene ring is actually electron rich ring, right? So if I attach any group, for example NO2 group, for example a CN group, or any group which is a electron withdrawing group, if I attach any group to the benzene ring which withdraws the electron from the ring, hence it does what, bacha? Hence it is making the ring electron deficient, right? Because it is taking away the electrons from the ring. So if you attach any electron withdrawing group to the ring, what will happen to the haloarenes? What will happen to the haloarenes? Beta, this is a English channel, so I cannot speak in Hindi. We have another channels, you can go and check them out. Okay? Vedantu do have a Vedantu JE channel, which is a totally Hindi channel. You guys can go and check it out. Okay, so this is electron deficient, making it electron deficient. So, bacha, in this case again, in such a case, when I've attached electron withdrawing group. For example, I attach one NO2, then I reduce the temperature, and also I'm not giving any pressure, so I've reduced the Darcy condition, and again substitution happened, and now I attach two NO2 groups. Now I again reduce the temperature, and again substitution happened. Now I attach three NO2 groups, and only with warm H2O. Now this Cl is getting replaced by the OH group. Can everybody see these reactions? So what was the first thing I told you? I told you that haloarenes do not show substitution reactions due to those following four reasons which we just talked about. But under drastic conditions, they can show substitution reactions. And also those, if you try to attach such substituents which are electron withdrawing, decreasing the electron density from the ring. Hence, the nucleophile can attack it much more easily. Hence, in those conditions, again, nucleophilic substitution reactions can happen. Correct? Correct. Now, can you see, the next question should be, ma'am, why have you only attached nitro groups at the ortho and the para positions, right? Only at the ortho and the para positions have I attached the nitro group for this reaction to happen. Why have I done that? But after forming the resonating structures, you can answer this question on your own. Form the resonating structure of this compound. Okay, what will happen? What will happen? This double bond will go here, the negative charge will go here. Okay, so can you see the movement of the negative charge when I'm drawing the resonating structures just like this? The movement of the negative charge is the ortho position, and then again at the para position and the ortho position, right? So can you see? Can you see? And the nitro group is what? The nitro group is electron withdrawing group. So can you see the carbon which is getting a negative charge through resonance, and I've attached the nitro group to the same position which is the ortho and the para, where it can withdraw that electrons. Hence, due to that, only ortho and para nitrobenzenes show this reactivity change. Okay? But if you try to attach at meta position, right? If you try to attach nitro at the meta position, can you see that the negative charge never resonates at the meta position? Hence, if you try to attach nitro at the meta position and try to conduct the experiment again, you will see no change in the result with the nitro at the meta position, because it is not able to extract the negative charge at the meta position. It is only able to do that at the ortho and the para position. Everybody understood this? Everybody understood this? Okay. Next is reactions of haloarenes. So what are the reactions of haloarenes? Bacha, only one kind of substitution we read which occurred under drastic condition. Now, what kind of reactions haloarenes actually give? They give electrophilic substitution reactions. Why do they give those reactions? So this is the haloarenes that we're talking about, right? Now, due to the resonating structures, they will get a negative charge on the ortho and the para positions that I've already told you. So this negative charge means what? Now they can attract some positivity in their life, right? They already have negativity in their life. So the positivity will be brought by some electrophile. Electrophile is something which is positively charged or is electron deficient. Correct? So they will show electrophilic substitution reaction due to this. Now, where will the incoming electrophile attack? Okay? Will it attack at the ortho or para position, or will it attack at the meta position? Okay? So can you see that even though, what kind of group is your halo group? Bacha, your halo group is actually slightly deactivating group. Now, what are deactivating groups? Any groups which actually decrease the electron density on the ring are called deactivating groups. Okay? They're decreasing the electron density of the ring. Okay? But, and they are also, halo groups also show minus I effect, and they also show plus R. Plus R means what? That they're showing resonance inside the ring. Minus I means what? Because they are a slightly deactivating group, so they take away electrons from the ring. So these two are the effects shown by the, even though they show minus I effects, still halo groups are actually ortho and para directing groups. Always and always remember that they're all ortho and para directing groups. ठीक है. Next is electrophilic substitution reaction. Number 4 that we're going to talk about is the halogenation reaction. So in this case, any halogen in presence of anhydrous FeCl3, again a very good Lewis acid. In presence of Lewis acid, if I try to react, I get a major para product and a minor ortho product. So where is this Cl attacking? The Cl is attacking the ortho and the para position, right? But the para product is more stable because it is least sterically hindered, right? It is very, very far away. There is no repulsion between them. Hence, it is the most stable and most formed. And the minor product is the ortho product. Okay. Next electrophilic substitution is nitration. Nitration, the reagents for nitration is HNO3 plus concentrated H2SO4. What is the electrophile? The electrophile is NO2 plus. Remember this thing. The NO2 plus attacks the ortho and the para positions. Similarly, sulfonation. Sulfonation, the electrophile is SO3H plus. Remember this thing. This is the electrophile and it attacks the ortho and the para position, and both the cases para is the major product. Right? The next haloalkanes haloarenes reaction is Friedel-Crafts reaction. What happens in Friedel-Crafts alkylation, bacha? What happens in Friedel-Crafts alkylation? Who can tell me? So, bacha, in Friedel-Crafts, it is again a very, very extremely great reaction. I just took a benzene ring. In benzene ring, I try to react with RCl. RCl in the presence of AlCl3, and what happens? The chlorine goes away and the alkyl groups gets attached over here. Friedel-Crafts reaction is two types: Friedel-Crafts alkylation and Friedel-Crafts acylation, right? In the acylation, what is happening? RCOCl is the reagent, right? And I'm trying to attach it on the benzene ring. It gets attached through this carbon on the benzene ring, and this R gets attached over here. Now let's know a bit more about the Friedel-Crafts reaction. So, bacha, in Friedel-Crafts reaction, again, what is happening? This was the Lewis space that you take. What was the Lewis space? RCl. Okay. RCl was the Lewis base. Why is it called the Lewis base? Lewis base is anything which is rich in electrons, right? And AlCl3 is a Lewis acid. It is anything which is deficient in electron, because AlCl3 only has 6 electrons in its outermost shell, right? Because it has only 6 electrons in its outermost shell. It means what? Yes, Rudra, you are absolutely right. You're absolutely right. Okay. Next is, it has 6 electrons, hence it is electron deficient because its octet is not complete. Therefore, this acts as a Lewis acid. The electrons from the chlorine attack the AlCl3 and they form, and finally it forms a tertiary carbocation and your AlCl3 minus. This is formed in the next thing. But can you see here that there is a formation of a carbocation in Friedel-Crafts alkylation reaction? So carbocations means what? Carbocations means now in this reaction we are going to attach that thing to the benzene ring which is the more stable. For example, here rearrangements can be done because carbocation is formed. So for rearrangement, what can we do? We can do hydride shift, we can do methyl shift. What I am talking about, I will let you know here. So here the electrophile is a carbocation. In Friedel-Crafts alkylation, the electrophile is actually a carbocation. Right? Now next here, where is the, I have not mentioned it. Oh no. Okay. So here in this case, what happens in the alkylation? You have to attack that kind of alkyl group which is the most stable. For example, tertiary or whatever rearrangements is possible in this reaction, which I've already told you. Limitations of Friedel-Crafts is what? Limitations is vinyl halides and aryl halides do not undergo Friedel-Crafts alkylation. Why? Because I again told you carbocation will be formed. So is vinyl carbocation stable? No. Is phenyl carbocation stable? No. Hence, this kind of alkylation will not be possible if the halides, remember this thing, these are we're talking about halides. If the halide that I've taken is a vinyl halide or a aryl halide, then Friedel-Crafts alkylation will not happen. Similarly, they do not work when strongly deactivating group is present. For example, NO2 is what? Electron withdrawing group. It is deactivating the ring. And we want the ring to be electron rich. Why? Because the electrophile has to attack. Hence, we want the ring to be very, very rich in electron. If you are removing the electrons from the ring, hence there will be no Friedel-Crafts alkylation reaction. Now we're talking about acylation. I just told you in acylation what happens. This is, for example, the benzene ring, right? And this is the CH3 C double bond O Cl molecule. What happens? This gets attacked over here, and the final product formed here will be COCH3, and HCl actually goes away. So this is the final product here, which is your electrophile. You should all know the electrophile in Friedel-Crafts acylation is the acylium ion. This is the acylium ion. Everybody look at this ion. CH3 C triple bond O, O plus. This is the acylium ion, which is your electrophile here. Right here, no rearrangements occur. In Friedel-Crafts acylation, no rearrangement occur. In Friedel-Crafts alkylation, rearrangements can occur, and you have to attack that kind of carbon to the benzene ring, which is more stable. For example, tertiary, secondary, whatever. ठीक है? No, bacha, they will not ask for mechanism of Friedel-Crafts. No, 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 no. In this chapter, the only mechanism that you have to focus on are SN1 and SN2 mechanism. That is it. That is it. Those are the only, and sometimes even beta elimination reaction mechanism can be asked. That is it. No other mechanism you have to focus on. This is just how to form the products for your basic extra knowledge, because I just can't help myself telling you guys everything that I know. I just try to reduce it every time, but I just fail. I just fail in just crisping down the information to just bits and pieces, because I hate it. I think as students you're going to encounter so many questions, and only after you see so many mechanisms your mind will open. Okay, because a carbocation is forming, that's why I have to attack it from this side. Oh, because the carbocation is forming, there cannot be an electron withdrawing group. So that's opening your mind. It's very, very essential at this point of your time. Now that's the Fittig reaction that we're talking about. Fittig reaction is similar as Wood's reaction. But in Wood's reaction, we did what? We were reacting RX. We were reacting haloalkanes. Here we are actually we're actually reacting haloarenes. ठीक है? Haloarenes it is here. Haloarenes with sodium in dry ether, and it will form a diphenyl compound. ठीक है? ठीक है? कार्बोकटाइन और रेडिकल का हाइब्रिडाइजेशन क्या होता है, प्लीज बता दो बेटा. कार्बोकटाइन का हाइब्रिडाइजेशन मैं एक्सप्लेन करके बताती हूँ ताकि आप कभी ना भूलो. कार्बोकटाइन का क्या मतलब है कि उसके पास 3 ग्रुप्स तो जुड़े होंगे और एक उसके पास वेकेंट p ऑर्बिटल होगा. ऐसा होता है ना कार्बोकटाइन. किसी ने पूछा, sorry, so somebody asked what's the hybridization of carbocation. So the carbon will be attached to 3 other atoms and it will have a vacant p orbital. So whenever a carbon is attached to just 3 atoms, it always has a sp2 hybridization. Remember this thing. Was that the question? And for the free radical, the free radical is somewhat like this. Free radical has what? 3 carbon atom is attached to 3 other bonds, and here it will be a free radical present over here, right? A free radical, it means what? It has somewhere between sp3 and sp2 hybridization. Nobody will ask you the hybridization of free radical, bacha, because its hybridization is actually in between sp3 and sp2, and when it will be sp3, when it will be sp2, that's a debate. Not a debate, but you have to understand a concept. I can make you understand, but right now we're not going to do that. But yes, carbocation has the hybridization of sp2. I hope I cleared your point. Yes, Rudra knows my one shots are really, really long, because chemistry, you have to know the basics of things in order to understand the bigger things in life. Chemistry is just like that. ठीक है? Otherwise, the chemistry will go from above your head. just like how most jokes go, right? And now we're talking about Wurtz-Fittig reaction. Wurtz-Fittig is what? When we use one haloarene ring and the another one haloalkane ring. Okay? When we use one haloarene, one haloalkane, and then join these two together, and here instead of X, this R will come, and we will get a Wurtz-Fittig product over here. So here we have completed the haloalkanes and haloarenes part. Now we are going to study about alcohols, phenols and ether. Let me know alcohols, phenols and ether. Please, can I go and have some water for myself? I will come back. Do not worry. Just give me like 2 minutes. I will just go. I'll give you guys just 60 seconds break. And we will do alcohols, phenols and ether after I come back. ठीक है, everybody? Yes, Wurtz plus Fittig. 60-second break is okay? Or do you want a longer break? Do you want a longer break? Please let me know what do people want, or we can come back after an hour. We can even come back after an hour to discuss alcohol, phenols and ethers. What do you want to do? What do you want to do? Please let me know in the chat box. I'm looking at the chat box. 10-minute break? 10-minute break or a 1-hour break? But today though there was no class going on. Why do you want a longer break? Long break, polyhalogen. Yes, somebody has asked for polyhalogen. Yes, you're right. I left the last page of your alcohols, phenols and haloalkanes and haloarenes because that's a theory part. There's just 2 pages left. Rest or everything I've covered. Those 2 pages are theory where they talk about the polyhalogen compounds. What are freons? What are DDT? And what are their uses, right? And there's and what are the enzymes used to convert? Acha, all these things. 10 minutes. ठीक है. I think the majority of the people want a 10 minutes break, so we will go with a 10 minutes break. We need to revise this chapter. Yes, bacha, you need to revise it on your own. That is a given. Okay? Whatever I've taught you, even if you go back, like I'll upload the notes as soon as the session is over. Even if you go through the notes, everything will be crystal clear in your head because you have learned everything already. I will give you not a 60-second, but a 10-minute break. I will be back. I will be back. Right now it's 3:36, so let's come back at 3:45. 3:45 we will be back. ठीक है? 3:45. ठीक है? Thank you so much. 3:45 back. We will be back. चलो. Hello guys, I'm back. 3:45 it is. We are back with alcohols, phenols and ether. I hope you understood few of the things that I try to teach with the haloalkanes and haloarenes that we completed. Right now, alcohols, phenols and ether. Again, it's going to be an extremely NCERT based thing because right now we're focusing on board exam. Let us go. So first screenshot from alcohols, phenols and ether, which talks about what are the uses of the alcohols, phenols and ether, right? So the ethanol is used as a spirit for polishing wooden furniture. The sugar that you eat, sugar is what? It is polyhydroxy compounds, right? The cotton that you wear, the paper on which you write, all contains the OH group. So these are some of the examples of that, right? Let's move on to the next introduction to alcohols. What are alcohols? So we are all familiar about alkanes, which have a RH group, right? So when we replace one of the hydrogens with the OH group, we get an alcohol. And if we do the same with the phenyl ring and we replace one of the hydrogens with the OH group, like this, for example, this is like this, right? Here I will replace one of the hydrogen with the OH group, right? Like this, then I will get a phenol. Extremely easy, right? This is alcohol and this is phenol. What are the differences here? Here the carbon is sp3 hybridized. Here the carbon is sp2 hybridized, right? Therefore, they're going to show different reactions. They're going to have different properties. Even though they have the similar functional group, the reactions, the properties are going to vary, and we are going to see in this chapter how they are going to vary, right? Okay. Next is general formula of alcohols. What is the general formula for alcohols? It is CnH2n plus 1 OH, right? Who can tell me what is the general formula for alcohol? It is obviously option A, CnH2n plus 1 OH. This is a general formula for alcohols. Now next is the classification of alcohols. Again, they can be monohydric, dihydric, trihydric depending on the number of OH groups in one compound. Here there is only one OH group, two OH groups and three OH groups. So it's a mono, di and trihydric alcohols. Right, number one classification. Number two, for the mono alcohols, the hybridization of the carbon matters. Right, so the compounds containing sp3COH bonds. Number first classification for monohydric alcohols. Can you see here the carbon? This is primary alcohol. Why? Because the carbon to which OH is attached to only one carbon. Hence it is primary alcohol. This carbon is here now attached to two carbons. Hence it is a secondary alcohol. And this carbon here is attached to three groups. Hence it is a tertiary alcohol. Everybody is familiar with these things? Primary, secondary, tertiary alcohols. All of them are sp3 hybridized. Let's move on to the next thing. Allylic alcohols. Allylic are what? Allylic is again sp3 hybridized carbon next to the C double bond C bond, right? For example, this is the sp2 hybridized carbon. What is the allylic carbon? So the carbon right next to the sp2 hybridized, which is sp3 hybridized, this carbon bacha is called the allylic carbon, right? Right next to the double bond, the carbon that exists, and if to that carbon OH group is present, then that is called a allylic alcohol, right? Here it is a primary allylic because this carbon is attached to just one carbon. Here this carbon is attached to two carbons and it is a secondary allylic alcohol. And this carbon is attached to one, two, three carbons and it is a tertiary allylic alcohol. Everybody understands this? ठीक है? ठीक है? Beta, why do they look like aldol to you? These are alcohols. Next is benzylic. Again, please be very, very vigilant with this term. Benzylic and arylic are different terms. If the alcohol group is directly attached to the benzene ring, these are called arylic alcohols, right? Arylic alcohols. And if it is attached, the alcohol group is attached to the carbon group attached to the benzene ring, right? Here then it is called, bacha, what? It is called the benzylic alcohol. Remember this thing again, they can be of primary, secondary, tertiary type. This is the primary alcohol. This is the secondary benzylic alcohol. This is the tertiary benzylic alcohol because this carbon is attached to 1, 2, 3 carbons. Okay, this thing is clear to everybody? This thing is clear to everybody? ठीक है. Next is compounds containing sp2COH bonds. The OH bond is attached to C double bond C. अब for example, if the OH group is attached to the sp2 hybridized carbon, for example here it is directly attached to the carbon containing the double bond called the vinylic alcohol, and if it is attached directly to the benzene ring, it is called the arylic or the phenols that we're going to study. And these are what? These are sp2 hybridized carbon. So this is the basic classification that you read about. Again, for phenols, they can be monohydric, dihydric, trihydric, depending on the number of OH groups present. These are simple classifications, nothing for me to explain. Next are ethers. So ethers, bacha, can be either simple or symmetrical ethers, or they even can be mixed or asymmetrical ethers, correct? So they can be between these things. 1 second. Okay. Now, bacha, what is happening? How to write the IUPAC name of the ethers? That is the main thing that students actually struggle in. So, bacha, how do you write the IUPAC name? For example, look at this ether. This is ethyl and this is methyl group. So, this is the ether group C2H5OCH3. This is how the functional group of ether looks like. There is an oxygen in between, and on the both the sides, what are attached? The alkyl groups are attached, right? Both the sides, the alkyl groups are attached, and that's how you form an ether compound. Okay, that's how you form an ether compound. And what is happening in the next case? How are you going to write the IUPAC name of it? How do you write the IUPAC name? Bacha, in ethers, the IUPAC name is written alphabetically. That is it. So whichever alphabet comes first, write that alphabet. So this is ether, this is ethane, right? This is ethane and this is a methane molecule. How to write its name? So whichever, for example, E comes first in alphabetical. So I will write ethoxy, ethane. That is it. That is its entire name. So that's how you write, or methoxyethane. You can write anything. You can either write it alphabetical wise, or even the largest number of carbon chain that is forming becomes the main parent chain. I'm going to explain to you just right now. Actually, forget this thing that I just said. Actually, we're going to study more examples with which it will be more clear to you guys. एक बारी forget this thing. ठीक है? But understand, ethers can be mixed ethers or simple ethers. Simple ethers means on both the sides there are same number of carbon atoms, and mixed ethers means a different number of carbon atoms are present. Okay. Now this is how you write the IUPAC name of alcohols. First of all, so to write the common name, what they have done, they've just written alkyl alcohol. Means what? This is the methyl group, so methyl alcohol. This is propyl group and propyl alcohol, right? So these are simple namings. You have to go through all of these namings. I've attached the screenshots over here. You have to know these namings, correct? For example, this molecule is tertiary butyl alcohol. Okay, this isomer of butane is called the tertiary butyl. And because this is alcohol, I have written alcohol. The IUPAC name you must be knowing. We learn it in 11th standard. Okay, next. Nomenclature of alcohols. So next is, this is a cyclohexane to which a OH group is attached, which is a cyclohexanol. This is a cyclopentane to which OH is attached, and the methyl is a substituent on the second carbon. Always remember that the primary functional group is given carbon number 1. So this will be carbon number 2. So it will be 2-methyl cyclopentanol. This is cyclohexanol. All is the suffix we used for the IUPAC naming of the alcohols. I'm not going to spend more time on this nomenclature because I consider this to be 11th standard part. But nomenclature will be asked in your exam. So please go through all these common names. Most important common names are this kind of compound where a methyl group and an alcohol groups are present together is called a cresol, and based on the position of the methyl group, it can be orthocresol, it can be metacresol, or a para. When they are far apart, it is a paracresol, right? And the common name of this compound where the two OH groups are close together on the ortho position is called the catechol. Where they are at the meta position is a resorcinol, and when they are at the para position is a hydroquinone. Extremely good common names can be asked in exams. Please emphasize on these common names. Next is nomenclature of ether. What will be the name of this ether? The common name will be dimethyl ether because two methyls are there, and at the end we write the ether group just like that. And the IUPAC name is methoxymethane. Here the IUPAC name will be ethoxyethane. Here the IUPAC name will be 1-methoxypropane. What it will be? First select the parent chain. The parent chain will be the one which has the largest number of carbon atoms. More number of carbon atoms will be the parent chain. I have selected the parent chain. Parent chain is selected only for the IUPAC naming. For the common naming, you just go alphabetical wise. For example, here it is methyl, here it is propyl, so the name will be methyl and propyl ether. Simple. For example, here it is benzene, here it is methyl, so the name will be methyl phenyl ether. That is it. Just alphabetically write the common name. But for the IUPAC name, you need to select the parent chain, and the parent chain will, the name of the parent chain will come as it is. For example, here it is propane, so propane, but the substituent will now become methoxy. For example, here the name will be ethoxybenzene. Benzene has more number of carbon atoms, so it becomes the parent chain over here, and the name will be ethoxybenzene. So just go through these names. I've taught you. For the IUPAC name, you have to select the parent chain. How to select the longest chain will be the parent chain. But for the common names, you just have to go alphabetical wise. ठीक है, alphabetical wise. IUPAC numbering bata for ethers. For example, वही तो I've taught you. For example, look at this molecule. This is a benzene ring is over here, and here 7 atoms are present. Can you see? It's a 7-membered chain over here. Hence, the parent chain will become this. Okay, so the name here will be 1-phenoxyheptane. The parent chain name comes as it is. It is a heptane. So heptane will come at the end, and this will become the substituent. It will be 1-phenoxyheptane. And similarly here, see, there is again a benzene ring over here, and a 1, 2, 3, 4. 4-membered chain, maximum number chain that you can form. So again, this will be the parent chain here, which will be a benzene, right? Benzene will be the parent chain. So here, how to do the numbering? Can you see? From this, from this oxygen, you have to start counting the number of carbon. This is carbon number 1, carbon number 2, and this is carbon number 3, right? And at the 3, there is a methyl group attached. So the common name, so the IUPAC name will be 3-methyl. 3-methyl. Then your substituent, which is your butoxybenzene. 3-methyl butoxybenzene. Everybody understood? Now look at this name. Here again, can you see? To this is the number 1 carbon, this will be the number 2 carbon. At the 2, there is what present? There is what present? Hanji. Okay? So you can again write it. The name will be 2-ethoxy-1,1-dimethyl cyclohexane. Cyclohexane. Because right now what they have done, bacha, what they have done now, because this is the parent chain. This is actually the parent chain. So I can consider this as number 1 and this as number 2. And at the 2 position, there is the ethoxy group present. So 2-ethoxy, and the parent chain is the cyclohexane. And on the 1 position, there is 1,1-dimethyl 2-ethoxy-cyclohexane. That is the name. Everybody understood? Everybody understood? Next, bonds and angles. Now the best part about the chapter start. The nomenclature is over. The basis of classification, the boring stuff is over. Now the interesting stuff which I like to teach is the bonds of. Why have I written bonda over here? What is a bonda, guys? Bonds and angles, right? We're discussing bonds and angles. So we're discussing bonds and angles of all alcohols, phenols and ethers. Okay, this is an alcohol, methanol is an alcohol, phenol is a phenol, methoxymethane is an ether. We're going to see the bonds and the angles in all of the cases. Now first look at methanol. Just focus on methanol compound right now. What do you observe? What do you observe here? That the structure that COH is forming. What is the hybridization of C over here? The hybridization of carbon here seems to be sp3, right? And even the hybridization of oxygen here is also sp3, right? So the combination is between a sp3 hybridized carbon and a sp3 hybridized oxygen come together and form a bond. Number 1 thing. Number 2, they are forming a tetrahedral structure. Can you see the oxygen is forming a tetrahedral structure? Tetrahedral structure. Why am I saying that? Because this is the oxygen, here's the hydrogen, Here is the carbon, right? And the two lone pairs will come over here and they form somewhat tetrahedral structure just like this. Okay? And what is the angle of tetrahedral? Everybody knows it is 109 degree 28 minutes. Now your question will be, ma'am, but this angle to they are forming 108.9 degree, which is a little bit less than the actual tetrahedral angle. Why is that the case? That is the case because as we know, the lone pairs on the oxygen, they have lone pairs. The lone pairs will call repulsion, right? The lone pairs will call lone pair, bond pair, repulsion, and hence due to that, this angle will come down and this angle will become a little less. These angles above the oxygen, okay? The lone pairs are causing repulsion to the bond lengths and hence the angle becomes smaller. Hence this angle is a little bit smaller. So this is all about the bonds and angles of the alcohol. Now come to phenol. The phenol, what kind of hybridization of this carbon is? This carbon is sp2 hybridized. Hence sp2 hybridized, right? And again, let's look at the oxygen right now. The oxygen again has two lone pairs. The two lone pairs oxygen and the hydrogen is attached over here. And here there is a benzene ring here, right? So it is again forming a tetrahedral structure only. Can everybody see that it is again forming a tetrahedral structure? What? The oxygen. I'm talking about oxygen right now over here. Okay. Now the only interesting thing, again the angle here is 109 degree because it is forming a tetrahedral angle. So it is 109 degree 28 minutes kind of equal to that. But the interesting thing to note over here is that this bond length, the CO bond, this carbon oxygen bond is actually smaller. Can you see this is only 136 picometer while here the carbon oxygen was 142 picometer. Why is that the case? Why is this bond actually small? This bond is actually small, bacha, because this is the phenol ring, right? And what will happen? The oxygen, the OH actually has lone pair of electrons. So it donates the lone pair of electrons and they go into resonance in this ring and hence this bond actually gains a double bond character, right? This bond actually gains a double bond character. Hence its bond length reduces in phenol. This is all about phenols, bond angles and bond length. Now come to ether. So ether again has a tetrahedral structure. Can everybody see? I'm talking about oxygen in all the cases. The oxygen here in all the cases is sp3 hybridized, has a tetrahedral structure, right? Now can you see if it is tetrahedral, ma'am, why is the bond angle more now? The tetrahedral bond angle is 109 degree 28 minutes, but here it is 111.7. Why is that the case? That is the case because can you see in ether there is a lot of alkyl groups. Can you see? And what these alkyl groups do? These alkyl groups cause repulsion, right? So due to this repulsion, what will happen? The angle increases. The angle increases a little bit due to the alkyl-alkyl repulsion. Okay? And the bond length here is approximately same as the OH bond, as the alcohol bond length. Okay? 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 Beta, I will teach you when to use. I've made a table. I know even when I was your age, I used to get so much confused between LiAlH4 and NaBH4. I've made a table. I will show you in what case you can use LiAlH4 and what case you can use NaBH4. Everything will be crystal clear right now. Just stay with me. Is this thing clear? Everything clear to everybody? Is this thing clear to everybody? Steric hindrance due to bigger sizes of alkyl groups. Yes, Rudra. Yes, Rudra. Okay? Okay, next is now we are back to the preparation of alkenes. Number for separation is from alkenes. How do we do that? We react alkenes with H2O. H2O in presence of acid. Okay, alkenes in presence of H2O in presence of H plus. What do we get? We get a reaction just like this. What will happen? To one carbon, H will go, the other carbon, OH will go. Okay, now or to which carbon the OH goes, to which carbon the H goes, depends on what? It again depends upon the Markov-Nikov rule. Okay, it again depends upon the Markov-Nikov rule. Okay, here what I'm doing, I've taken an alkene, I'm trying to react it with water in presence of acid. Okay, so I have to add two things here now, OH and H. So I will add OH to the more substituted alkene, which means what, the alkene around which more alkyl groups are present. Okay, I will choose that carbon atom which is a secondary or a tertiary carbon atom, है ना, which is a secondary or a tertiary carbon atom. I will choose that to attach my OH, and to the other carbon the H will go. Okay, just like this. This is again a addition reaction. What kind of reaction this is? Addition reaction. Okay. Now this mechanism is extremely important. There are few mechanisms that have the possibility to get asked in a board exam. This is one of them, very, very important reaction mechanism. So we are talking about what? We are talking about preparation of alcohols by acid catalyzed hydration of alkenes. So I took a alkene and I took water in presence of acid, H2O and H plus. Then what do I get? I get a H3O plus. Okay, I get H3O plus molecule. Now what will happen? This is a double bond over here in alkene. Double bond means what? There's a pi bond, means it is electron rich. So electron rich species will want to do what? Will want to attract any positive cation towards it. Right? So what it will do, this species will attract this H, right? Will attract this H and attach a H over here, and it itself will become a positively charged species over here. It itself will become a carbocation. And then here, if the rearrangement of carbocation is possible, then it will happen, and it can form a primary, secondary, tertiary carbocation over here. Then the H2O again attacks as a nucleophile. Why is it a nucleophile? Because it is electron rich. Anything which is electron rich or negatively charged behaves as a nucleophile. Nucleophile attacks the positively charged carbon, and the OH gets attached over here. And then finally again deprotonation happens, and finally you get a result looking just like this. This reaction mechanism is extremely important. First step is you make a hydronium ion by reacting H2O with H plus. Then you attack the double bond to the hydronium ion. Then you form a carbocation. After forming the carbocation, you cause attack of the nucleophile. And then in the last step, again the proton is lost and the final product is obtained. Okay? Next is, in the following reaction, what can be the possible products? You have to write all the possible products and also tell me the major product of this reaction. Who can tell me? Who can tell me? Does everybody know how to perform this reaction? So I just told you that here with H2O and H plus, what will happen? There will be an addition of an OH as well as an H. OH will go where? OH will go on that carbon which forms the most stable carbocation here, right? So I'm again writing this down like CH3, C, and here it will be CH3. Here it will be again CH3. Here it will be CH double bond CH2. If I attach a hydrogen over here, right, then this will get a positive charge. So what I'm getting, that this carbon can get a positive charge, but this carbon is what? It is a secondary carbocation. But there is a possibility of forming a tertiary carbocation in this case. Ab you'll ask me, ma'am, how and where are you seeing this possibility? So bacha, if I do a 1,2 methyl shift, what I'm doing a 1,2 methyl shift. So I just took this as CH3, here it will be C, here it will be CH3 again. Okay, here I shifted this methyl to this carbocation, here CH, here I shifted it to CH3, and here it was CH3 again. And here what I did, here I made the carbocation. Now can you see, this is how I formed a tertiary carbocation now. Now to this tertiary carbocation, this OH can now attack, and this will be the major product form. So can you see, whenever there is a carbocation forming and there is a possibility of rearrangement, please do that, because that would be the major product. Let us look at all the products that can be formed. First product is that the OH can be attached to the primary carbocation. This will be the most minor product. Remember this thing. formed in 0.112%. That's it. Okay. Next is with the methyl shift, the major product is formed, which I just showed you how to form that. And the next is again the secondary carbocation product, which will again be a minor product, but its percentage can vary from 10 to 15%, but this will be the major product. Everybody understood this? Next, hydration. Now that I taught you hydration, what will be the stereochemistry of it, ma'am? So, bacha, hydration is not stereoselective, which means what? I was adding two things to the double bond, right? I was adding, one of the thing I was adding was OH, the other thing was H, right? I was adding two things to the double bond. Now, where will that both the two things attack from? Will both of them attack from the front? Will both of them attack from the back? Will one of them attack from the front, another one from the back? So, beta, after studying the stereochemistry of this reaction is actually not stereoselective, which means what? Which means the attack can happen from anywhere and everywhere in any way possible. It is not stereoselective, so you cannot say it is a syn addition or anti-addition. Nobody can, because every kind of addition happens, even the syn and the anti. What are syn? Syn is beta when the OH and the H, both of them attaches from the same position, right? And the anti-addition is, for example, OH attacks from the front while the H attacks from the back. That is the anti-addition product. And if both of them attack either from the front or either from the back, those are syn addition products. Everybody understood this? हाँ, sin भी होगा, anti भी होगा, you are right. Next, even intramolecular hydration of alkene can happen in one condition, beta, कि 5 or 6 membered rings are formed, because these are only stable. 4, 3, never make those rings because those are not stable. If 5 or 6 membered rings are formed, intramolecular means what? See, in the same molecule, you have a OH group as well and a alkene group as well, right? So what can happen in presence of acid? This OH group will do what? This OH group can get in the presence of acid, this can get protonized, right? The OH group, and then it can attack this double bond over here and form a 6-membered ring just like this. Okay? Now the preparation of alcohol. I just taught you one kind of preparation, which was what? Where rearrangement was happening. Remember, the most stable carbocation with the rearrangements was happening. Okay? With the acid catalyzed alcohol, that's how we were preparing from alkenes. Now if I tell you from the alkenes, you are again making alcohols, but the reagent is changed. The reagent is oxymercuration, demercuration. The reagent is HgOEC2 in presence of THF and H2O. Okay? And second is NaBH4 in presence of OH minus. Right? So oxymercuration, this reaction is called oxymercuration, demercuration. This again, bacha, happens according to the Markovnikov. I just written over here. It follows the Markovnikov addition, which means what? That the OH will attach the more substituted carbon. Right? Right? But here what happens, bacha, this is a Markovnikov reaction, but here no carbocation formation happens. Hence, if you want to get a product which is a Markovnikov true product, okay, which follows Markovnikov rule, but there is no rearrangement happening, then you can use oxymercuration, demercuration. Okay? This is a two-step mechanism, and the addition of H2O is anti here. Anti-addition means if the OH attacks from the front, then the H will attack from the back side. So this is an anti-addition of H2O. And why are they saying H2O, bacha? Because we are actually attaching H2O, right? I'm attaching OH here and I was attaching H over here. So it's a H2O addition in general. So it follows Markovnikov rule, but because no carbocation is formed, hence no rearrangement happens. And this is an anti-addition. Next preparation again from alkene is the hydroboration-oxidation of alkene. Extremely important reaction. Here the reagent is B2H6 and THF in presence of peroxide and OH minus. Right? Here again, bacha, here again the addition actually happens through anti-Markovnikov rule. Remember, again we are attaching OH and H, but the here addition happens to anti. Can you see? The OH gets attached to the primary carbon over here and the H attacks the secondary. Correct? So this is an anti-Markovnikov attention with the OH attaches to the primary carbon. Right? And here again no carbocation is formed. This is a syn addition. Syn means what? Both the OH and the H attack from the same side. Attack from the same side. Right? And here the alcohol is obtained in excellent quantity given in your NCERT. If anybody asks, here the alcohol is obtained in excellent quantities. Okay? Now hydroboration or oxidation mechanism is given in your NCERT. So please, all the mechanisms are given in NCERT. Please thoroughly practice them. What is happening? This is B2H6, right? So B2H6, what happens? So this is the alkene molecule and it gives one of the hydrogen to here. So hydrogen attaches over here and BH2 attaches over here. Then again another alkene atom comes and then again similar reaction happens. So one by one, each of the hydrogens of the BH3, right? Each of the hydrogen of this molecule BH3 gets replaced by another alkene molecule, and at the end with the presence of peroxide, what happens? You get an anti-Markovnikov product. This is the reaction mechanism. Everybody understood the reaction mechanism? Okay. Next, by action of cold dilute alkaline KMnO4, syn dihydroxylation and Bayer's test. Again, we're talking about alkene. With alkene, I'm using H2O in presence of oxidizing agent. Any oxidizing agent, for example, here we have taken alkaline KMnO4. What I'm getting? I'm getting a vicinal alcohol. Can you see? This is a vicinal alcohol when the OH groups are attached ekdam just right to each other, right? This is a vicinal alcohol. I'm getting, the name is glycol, right? So with glycol, this is called the Bayer's test. Bacha, what is called Bayer's test? Why is it called Bayer's test? Because can you see the alkene is getting converted into a vicinal dialcohol, right? So the name is ethane diol. Alternatively, you can use another reagent with this osmium tetroxide in the presence of sodium hydrogen sulfate. Okay? Here again the addition happens, but here bacha, the addition, what kind of addition happens here? Here a syn addition happens. Alternatively, this also you can use. There are two reagents for the same reaction. For the same reaction, you're making alcohols, but with this case, you get dialcohols. You get diols, right? Now next, using peroxy acids or anti-dihydroxylation. Okay? Beta, this is your alkene and you are now using peroxy acids. Peroxy means what? Whenever anything contains total number of 3 oxygen atoms in between. Can you see that this peracetic acid has 1, 2, 3 oxygen atoms in between. Trifluoroperoxytic again has 1, 2, 3. MCPBA, which is metachloroperoxybenzoic acid, again has 3 oxygen atoms in between. So all of these, any compound, no matter what compound they give you, but if they have this kind of structure, which is C triple bond O structure, then those compounds are bacha your pakka peroxy acids, right? Those are peroxy compounds, those are peroxides or peroxy compounds, right? So when you try to react alkene with the peroxides and again OH, then again vicinal alcohols will be formed, but here the addition will be anti. Do you remember in the last case here we were doing syn addition? Here we are doing anti addition. Anti means what? One OH will come from below, the other OH will come from the above or from the front or from the back. Okay? So both the OH will come from the opposite direction. Next, for example, if I'm using MCPBA, I just told you this is a peroxy acid. Hence, how will the OH attach here? There's an anti-addition. One OH comes down, one OH goes below, and the addition happens on the double bonded carbon. Just remember that. Okay, and because of that, you will also get a mirror image. Next is solving these questions. Find the final products of the following reactions. Who can find the final product? Now, I told you, I am naming all these carbons one by one. This is carbon number A, carbon number B, and carbon number C. Okay? And this is the first reaction, this is the second reaction, and this is the third reaction. Who can tell me with which reagent on which carbon OH will attach? With H plus H2O, where will the OH attach? With oxymercury demercuration, where will the OH attach? And with B2H6, where will the OH attach? Who can tell me for the first, second, third, where will the OH go? Where will the OH go? Who can tell me? Who can tell me? I am looking at the chat box. I am looking at the chat box. First one where, bacha? First is B. Tell me like this. First B, second C, third D. Tell me like this. What is AB? What are you trying? First B. Okay. Nitish is saying first B. First B. Why are you saying that, Nitish? Look at the most stable carbocation. Here in this case, rearrangement can happen. Rearrangement can happen. Remember this. So the most stable carbocation formed. Which will be the most stable carbocation? Nobody has given me the correct answer yet. Okay, Vitesh Sugadev. Vitesh Sugadev and clashing with Naveen Kumar, NJ Tamil and Vitesh Sugadev have given the correct answer. That's it. Only two people. Only two people among so many people have given the correct answer. Bacha, here we have to look on the first rearrangement can happen, right? And which will be the most stable carbocation. Can you see if I put a positive charge over here, this actually becomes a benzyl carbocation, which is extremely stable. Hence, the OH in the first case will attach over here. Very, very good. And similarly for the oxymercuration, demercuration, I told you, Markovnikov rule, but no rearrangement. Hence, these will be the products. Look at this. The first OH attaches on this carbon, the second OH, because here with oxymercuration, demercuration, Markovnikov product forms but with no rearrangement. Hence, the OH attaches over here. The OH will come over here. And with B2H6, the OH goes anti-Markovnikov. Hence, it goes to the primary carbocation. Everybody understood this? Everybody understood this? No, bacha, the chapter is not completed yet. Now, who can answer this question for me? Alkene can be converted into alcohol by which reaction? By which reaction? By which reaction? Who can tell me? It is a which reaction? This is a addition reaction. I just told you nobody is answering. Nobody is answering. Okay. Okay, cool. Cool, students, cool. Beta, anti-Markovnikov means when the OH attaches to the least stable carbocation. Just look at this like that. Okay? For example, if the double bond is here, so there are two possibilities of the OH to attach. Somebody is asking, ma'am, what is anti-Markovnikov rule? Okay? Anti-Markovnikov is what? For example, I have to attach OH. There are two possibilities. Either I can attach on this carbon or on this carbon. Right? So can you see if I attach OH on this carbon, which is the secondary carbon, if I attach on here, then the OH will be surrounded. This carbon is actually a more substituted carbon, which means what? It is surrounded by two other carbons. Right? So this if the OH attaches over here, this is called the Markovnikov product. But if there is another possibility that the OH can attack over here, over this side of the benzene. So here if the OH attaches, which is the least substituted carbon, right? Because it is only covered by just one more carbon, right? It is the least substituted carbon. Hence this addition is called the anti-Markovnikov addition. If the, for example, which happens with the B2H6 case. Okay? Next is preparation of alcohol from carbonyl compounds. Carbonyl compounds can also form your alcohols. How? Carbonyl, by undergoing reduction, right? If I reduce your aldehyde ketone carboxylic acid, I can get alcohols. See, here I have taken a aldehyde and I am reducing it with any reducing agent. For example, what can be the reducing agent? It can be H2 nickel, PD. Somebody was asking me, ma'am, where will LiLH4 be used? Where will NaBH4 be used? I told you I will make you understand in a table. So it will come right in this topic. So please stay here with me, right? Please stay here with me. So here what will happen, bacha? Aldehyde gives primary alcohol. Okay, with the reducing agent, either it is a aldehyde or a ketone. If I reduce it, then I will get a alcohol, right? What are the reagents used? The reagents can be H2 on nickel, palladium or platinum. The next reagent are LiLH4 or NaBH4. Okay, to reduce aldehyde and ketone. अब aldehydes get reduced to primary alcohols. Look at this. ठीक है, aldehydes give primary alcohols while the ketones always give secondary alcohols. Remember this thing. ठीक है, and the similar reaction can happen with LiLH4 and NaBH4. But remember that LiAlH4 cannot reduce the alkene, alkyne and benzene ring. ठीक है, because alkene, what is alkene, बच्चा? Alkene looks like this. ठीक है, it can also gain hydrogen atoms and get reduced, right? But LiLH4 is not able to do that. LiLH4 cannot reduce alkene, alkyne and benzene rings. It can reduce all the other things that we're going to talk about. Next is carboxylic acid. From carboxylic acids also you can get alcohols, but you need, bacha, what? You need strong reducing agent with carboxylic acid. ठीक है, strong reducing agent ALH4 is a very good, very strong reducing agent. It directly converts carboxylic acid to your alcohol. ठीक है, I will tell you one funda. What the funda is, कि for example this is your alcohol, right? And if I oxidize it, if I oxidize my alcohol, I will get what? I will get a aldehyde or a ketone. ठीक है, I'm just writing carbonate. I'll get a aldehyde or a ketone, and if I oxidize it further, I will get a acid. ठीक है, now move ulta. Now move reverse. Now if I want to reduce aldehyde, I'll get a aldehyde or a ketone, and if I want to reduce aldehyde or a ketone, I will get a alcohol. ठीक है, reduce. So this funda you should remember. So now what I'm doing, I'm trying to reduce carboxylic acid directly to alcohols. Can you see carboxylic acid directly to alcohols? Therefore, I need a very strong reducing agent in order to do that. So LiH was a very good reducing agent which reduces COOH directly to CH2OH. ठीक है? And with the acids or any acid derivative, could be acid halide, could be acid anhydride, could be ester, could be acid chlorides. With all of these things, you will always get primary alcohols. Remember that. With acids or acid derivatives, you will always get primary alcohols, right? So this is your acid. Now the next reaction that they have shown here is that sometimes what happens, this LiAlH4 is actually a very expensive reagent. This is given in your NCERT, that's why I explained to you, and hence it is not used casually just for little conversions. So what is instead done in a commercial level, that they take carboxylic acid and then they make a ester of it. Okay, they'll react alcohol with it and they make an ester, and that ester can now be easily reduced with just hydrogen and catalyst to the primary alcohol, right? So did you understand this reaction? So this is how they eliminate the use of LiH4 because it is a very expensive reagent. Okay, the next is the NaBH4 and the LiAlHBH4 comparison. So I mentioned that both of these reagents can be used to reduce the things. So NaBH4, what can NaBH4 reduce? NaBH4 can reduce your aldehyde, can reduce your ketone, can reduce your acid chloride as well, but it cannot reduce carboxylic acid and your esters. Remember this thing. Similarly, LiLH4 can reduce everything, and similarly H2 nickel also can reduce everything. ठीक है, तो H2 nickel and LiLH4 are actually very good strong reducing agents, but NaBH4 is a mild reducing agent because it cannot reduce acid and esters. Correct? Everybody understood this part? Everybody? Yes, bacha, what is your question? Sorry, I get busy in teaching. Sometimes I Forget to look at the chat box. Beta, what is your question? Ask me the question of Babi Sudha. What is your question? Now next, again, more questions are asked from this thing as well. So, ma'am, you are saying that we are, what we are doing, achha, I have taken an aldehyde, right? So, let's go back here. What we are doing to this aldehyde. Let us look at this aldehyde. To this aldehyde, I'm doing one thing. I'm adding an hydrogen over here and I'm adding an hydrogen over here as well. Okay? So, I'm actually adding two hydrogens when I'm trying to reduce an aldehyde or a ketone, right? I'm trying to add one hydrogen to the oxygen and one hydrogen to the carbon when I look at the reaction after looking at the product. Okay? Now, where does this hydrogens come from? Okay? Now, let's look at the reagent NaBH4. So, NaBH4, the hydrogen from NaBH4 actually goes through to the carbon, and then the reagent, the water that the solvent that you're using, for example, here you're using D2O, and that oxygen will now take this D. Okay, so this is how the reaction, you don't need to know all the steps. This is the main the crust of the reaction mechanism. You just need to know that. For example, same in the LiLH4, this hydrogen only carbon will take, and the solvent that under which you're performing the reaction, that solvent will be taken by the oxygen. Same case as your NaBH4. So NaBH4, LiH4, this is how even the solvents are necessary. They can change the solvents and ask you for about different products. ठीक है? Beta, LiLH4 is a reducing agent. Next, from Grignard reagent. Again, from the Grignard reagent, you can again make alcohols. How can you make alcohols? For example, this is your carbonyl compound. The carbonyl compound bacha has what in it? This has a positive charge on it. This oxygen has a negative charge on it. Okay. Now, because this carbon is attached to a highly positive magnesium ion, hence this carbon gains a delta negative charge on it, and this attacks this carbon and forms a duct like this, right? And then this breaks off here and forms this compound. Everybody is following me? Everybody is following me? Everybody is following me? Okay, what is happening when I'm trying to react it with Grignard reagent? The R attacks the carbonyl carbon, right? The R attacks over here, and again through the solvent the H goes over here. The same case that we were doing before. Okay? From before, I was again converting the carbonyls into your alcohol. So I was using various reducing agents. But here I'm again converting carbonyls to alcohol, but right now using RMgX. So here the R attacks the carbon, right? So R attacks the carbon, so it will form C. Here it will come R, and here single bond, and this O. The H that comes on the O, this H that comes on the O comes from the solvent, which is H2O. Again, please understand this concept. Do not forget these concepts. ठीक है? Yes, correct. Next, from reactions involving Grignard reagent. Now again, what can you form out of these? So if you are using a methanol, remember, only and only when you are using a methanol and an RMGX, only and only then you can get a primary alcohol, right? And if you are using any other aldehyde other than methanol and Grignard reagent, then you will always and always get a secondary alcohol. And if you are using a ketone, then you will always and always get a tertiary alcohol with Grignard reagent. Why? Because one of the R will attack to the carbon and the H will attack the oxygen here, right? So this is how these reactions are done. Okay? Now in text question, who's going to do this question for me? Show how are the following alcohols prepared by the reaction of a suitable Grignard reagent. How will you prepare this reagent on methanol? So you already have a methanol with you. Methanol is what? It is C double bond O, and here it is H, and here again it is H. So on methanol, you want a Grignard reagent to form this compound. What Grignard reagent will you use to form compound number 1? The Grignard reagent should be CH3, C, CH3, H. Here it should be CH2. Okay? CH2 is already there, so we will not take this. Sorry. Okay, this and here will be the MgX part. Here it will be the MgX part. Okay, now what will happen? This will have a delta negative charge on it because this has a delta positive on it. So this carbon also has a delta positive on it. So this delta negative attacks this carbon and it forms a tertiary kind of compound, which is this compound that we have formed here. Okay, so this is the Grignard reagent that you use in this case. And what will be the Grignard reagent in the second case? In the isopropyl magnesium halide. Very good. Very good, Rudra. Very good, Rudra. Isopropyl clashing with Naveen Kumar also has answered. Very good. Sorry. Again forgot to bring water bottle here. Cyclohexane magnesium, very good. Very good clashing with Naveen. Very good. And even cyclohexyl. Correct, Rudra. Both of you are very correct. Very correct. Very correct. Okay? Malab, you understood the concept, right? Now, next question. Next is preparation of phenols. How can you prepare phenols? So, we are trying to prepare phenols from haloarenes. So, I reacted haloarenes with NaOH under these drastic conditions. Then what I'm doing, I'm actually you remember this will give the OH negative ion, which is a nucleophile. But haloarenes did not give nucleophilic substitution reaction unless they're in drastic conditions. Can you see? So conditions are very drastic and this gets replaced by ONA molecule, right? ONA it gets replaced by, and again when I try to neutralize it with acid, I get a phenol molecule. So this is the number one preparation method of from haloarenes. Next is from benzene sulfonic acid. How can you prepare? You take a benzene, you try to react with the oleum. Oleum is what? It is an acid of a sulfonic acid. Okay, sulfonic acid, and then the SO3H will get attached over here. Okay, and then again in presence of some base, what happens? This actually leaves, and only OH or a phenol is left over here. Extremely good reaction. You don't need to know mechanisms because it is not given in your NCERT. Basic reactions are given. You should know what are the preparatory methods. You know, even these kind of questions can be asked. Write 4 preparatory methods of phenols. So you should know all of these methods. Please practice writing down in your notebook. Okay, bar, repeatedly. Only then you will understand. You still have time. I'm still telling you, for the board exam, 2 days are more than enough. More than enough to just nail your NCERT, nail your board exam, because your syllabus has already reduced. Just 10 chapters, guys. Just 10 chapters. You still have time. If you still haven't started, I mean, obviously, you can forget a few things here and there. So I will not promise 90 plus, but I can promise that 80 plus, if you just start studying right now, you can score easily because the paper is very direct from NCERT. If you know basic things, if you start practicing even now, and if you're very sincere and you have just given up on everything else in life, then you can definitely score 80 plus marks. It's not that difficult. Especially, it's the easiest exam of your life, but very easy. Next is from diazonium salts. From diazonium salts, how can you form phenols? I took aniline. I reacted with NaNO2 and HCl at a very low temperature. Then I form a diazonium salt. With the diazonium salt, I reacted with warm water and I get phenol, nitrogen and HCl. Very important reaction. Next is from cumene. Again, a very important reaction asked so many times in your board exam. Favorite question of your examiner. So this is the structure of cumene. Cumene is a benzene ring attached with the isopropyl substituent. Okay? And then you react cumene with oxygen. What happens? This carbon actually becomes a carboxylic acid carbon. Then when you try to hydrolyze it in acid, you get a phenol product and an acetone product. And here both the phenol and the acetone are obtained in equal quantities. I mean, both the products are the major product of this reaction, and you get a good yield of even acetone in this reaction, even though if it is a byproduct. Okay? Next is physical properties of alcohol. What are the physical properties? So, bacha, for alcohol, Why will what would affect more? What would be the reason behind its properties? It would be the functional group, which is OH, right? It would be the functional group, which is OH. Okay. So the state, lower members are liquid while higher members are waxy solids. Remember this thing, that lower members are liquids while higher are waxy solids. Color, they're almost colorless. Odor, they have a faint odor except glycerol. Solubility, they're completely soluble in water due to H bonding. Molecular weight, ऐसे जैसे it will increase, solubility will decrease. ठीक है. So बच्चा, alcohols are completely soluble in water because they can form hydrogen bonding, and solubility also depends on their molecular weight. As the molecular weight increases, solubility decreases. Flammability, they are flammable with blue non-smoky flame. Boiling point, they have higher boiling points with comparative. Again, what is the reason behind boiling points? Is their hydrogen bonding. Okay, for solubility and for the boiling point, the reason is their hydrogen bonding, due to which they are very, very high. Okay, first physical property, boiling point. Boiling point is directly proportional to the molecular weight. As the molecular weight increases, then the van der Waals forces will increase. Remember this thing, and hence the boiling point will increase. Next, boiling point is actually inversely proportional to branching, which we discussed before also. As the branching increases, it means the molecule is becoming more in a circular shape, reducing the surface area. Hence, the van der Waals forces reduces. Hence, the boiling point also reduces. Yes, bacha, all the reactions are important. Beta, 90 plus depends on how much you already know. Somebody is saying, ma'am, can I score 90 plus in 2 days? If you have a basic idea of every chapter, right? Basic, or especially if I'm taking such longer session for you guys, I could have just taught you both the things in like 2 to 2.5 hours, which actually I predicted for myself, right? But I could have gone the shorter way and just told you the basic idea of these chapters. But I'm not doing that, because I know there are few students, even though in a pool of 200, 300 people, there are going to be 100 people who are going to stick around and who will be studying with me, revising everything with me. So I know how crucial each and every point is, right? So please revise it with me, and after it is done, revise it again on your own. Write down the reactions. I'm telling you, once you listen to someone, you grasp the concepts even better, right? Next is this quiz. What is the correct order of boiling points of alcohols having the same number of carbon atoms? Who can tell me this? Who can tell me this? What is the correct option? A, B, C, D. A, B, C, D. What will be the correct option of this? आवाज नहीं आ रही मेरी? Somebody is saying आवाज नहीं आ रही. Can you let me know कि मेरी आवाज आ रही है कि नहीं आ रही? B, A, B. Rahul is saying, Ragul is saying B. David is saying A. Nitish A. Clash A. Kanan A. Okay, so many A and a few B's. The correct answer is bacha option A, obviously, because as the branching increases in tertiary, what happens? How do you write tertiary alcohol? Tertiary alcohol looks like this. Tertiary alcohol looks like this. Can you see there's so much branching and it is formed the circular shape? Hence, its boiling point will reduce, right? Its boiling point will reduce. Hence, the answer is A. As the branching increases, boiling point decreases. Remember this thing. Now, the physical property, again, the boiling point we are talking about. So, it is mentioned here that boiling point of alcohols is actually so much more than even ethers, haloalkanes, haloarenes, and even of not the only alcohols, even phenols, boiling point is so high. Why is that the case? That is the case due to the presence of hydrogen bonding in alcohol. You know about hydrogen bonding, that hydrogen forms bond with more electronegative elements like oxygen, fluorine, and nitrogen. That is it. Only with these three elements it forms strong hydrogen bonds, which are very strong, difficult to break. And due to these H bonding which are formed both in phenol also, can you see the H bonding is formed, and even when phenol is in contact with the alcohols, normal alcohols, it again forms hydrogen bonding. Correct? Due to this, they have very, very high boiling point. Next, who can tell me which has the highest boiling point among these three? Ethanol, methoxymethane, and propane. I just told you that ethanol, due to hydrogen bonding, has the most highest boiling point than the methoxymethane and then your propane. Even though all of them have the same mass, have the same. See, it also contains two CH2 groups. This also contains two carbon groups. This also contains two carbon groups, but this will have the highest boiling point. Correct. Now, arrange the following compounds in order of the increasing boiling point. Very, very interesting question. Example 7.3. Again, a homework question. Please look at this example given in NCERT. Very good example. One or two of your doubts will get clear solving this question. I'm again mentioning you this. Okay? Next is solubility. These are extremely soluble, highly soluble in water. Why? Because they can form hydrogen bonds with water as are shown here. Again, this is why they are more soluble. Okay? And okay, solubility. Acha, just do B question for me. B question for me we can do. B part of the 7.3 question we can do right now. We can do right now. Who can tell me? Boiling point of B. I'm looking at the chat box. Who can solve the B question? Pentane, 1-ol, N-butane, pentanol, and ethoxyethane. We have to arrange in order of their boiling points. In order of their boiling points. Right now, I'm getting a little bit tired. I've been standing since 1 p.m. It's going to be 5. Okay. I'm looking at the chat box. Please answer, bacha, for the B part. For the B part, N-butane, ethoxyethane, pentane, and pentane 1-ol. Okay. So, bacha, I'm going to tell you once again. The highest boiling point will be of the alcohol, which is this. So, I'm writing this 1. This is N-butane is 2. Pentanol is 3. And ethoxyethane is 4. Right? So, the highest boiling point will be of pentane. Okay? And then the boiling point will be of your pentanol or ethoxyethane. Who can tell me? It will be of pentanol, right? Then it will be of your ethoxyethane and then it will be of your butane. What was your question? Sorry, I missed it. Sorry, I missed it. Your question was, Clashing was asking, ma'am, propanol or acetone has more boiling point. I saw acetone has more in NCERT, but fact says propanol should have more. But then whenever such kind of clashes happen, right, then please go with whatever NCERT is telling you, because for all your exams, whether it's JE, whether it's your board exam, they follow the NCERT pattern, right? And I also have confusion in that thing, which you have a confusion in. If I get the extremely correct answer of it from somewhere, I will let you know. But right now, I am also confused in that thing. Okay? Next. Okay? We have done this. Now, next is reaction of alcohols. Alcohols, bacha, show two kinds of reaction. One involving the COH bond and one involve the breaking of OH bond. Remember, two kinds of bonds can be broken. So, I'm going to tell you one interesting way how to remember these. So, bacha, if I break away the OH from the this. So, how will the OH break away? The OH will break away in the form of OH negative ion, right? So, OH will break away in the form of OH negative ion, which means it will leave behind a positive carbon, right? It will leave behind a positive carbon. And we know what kind of reactions can this carbon now perform. This is a positive carbon. So, it will give you what kind of reactions? Electrophilic reactions or nucleophilic reactions? Who can tell me? Hana? This can give you electrophilic reactions because this will now act as a very, very good electrophile. So, this will give you now electrophilic electrophilic reactions. So whenever COH bond is broken, it will give you electrophilic reactions. And when this OH bond is broken, okay, this is the formula for alcohol, right? COH. So sometimes this bond can be broken, sometimes this bond can be broken. And if OH bond is broken, how will it break? It will break like H will leave as H plus and O will stay as O minus, right? So now O minus will behave as a very, very good nucleophile, nucleophilic. This will give very, very good nucleophilic reactions. Hence, alcohol shows both kind of electrophilic as well as nucleophilic reactions. Why? Because of this reason, because both kind of bonds can break, COH bond and OH bond. Correct? Everybody understood this? ठीक है? No बच्चा, ether's boiling point is not greater. अभी तो बताया. Ether nahi. The boiling point of alcohol is the most, then it is your pentanol, which is your aldehyde, then your ether, and then your normal alkane. This is the order of boiling point. Please don't get confused. Now next is reaction of alcohol. So the two kinds of reaction that I just told you about. For example, here the oxygens lone pair are attacking the positive over here. So here the oxygen is behaving as a what? It is behaving as a nucleophile, right? So it is giving nucleophilic reactions. Similarly, the other kind of reaction is what? The other kind of reaction is that it can behave as a here. Can you see? Okay, perfect, perfect. Okay. Here again what is happening, this will leave as OH2 plus and the Br is getting attached over here. So it is showing this is what? This is again a nucleophile. Hence this is acting as a electrophilic center, right? So this carbon is acting as an electrophilic carbon and here the oxygen is acting as a nucleophilic oxygen. Remember this thing. So alcohols show both kind of reactions, nucleophilic and electrophilic. Okay. Next is reaction of alcohols. Reactions involving cleavage of OH bond. So I'm cleaving this bond, H bond. So bacha, whenever this bond is cleaving, it means what? It is leaving behind H plus ions. H plus is what? H plus. But if any compound gives H plus, it means what? We are talking about its acidity. Correct? We're talking about its acidity. Ab reaction with metals we are going to talk about. For example, I just took a alcohol, okay, and then I react with metal. So whenever anything reacts with metals and it gives away hydrogen, it proves that compound was acidic because it can give away H plus ion. So if you are trying to react anything with metal and you get hydrogen gas somewhere, it means that thing is acting as a very good acid, right? So reaction with metals, because the reaction is happening, it proves that the alcohols are actually acidic in nature. Similarly, see, look at the tertiary butyl alcohol in presence of another metal, which is aluminium. The reaction with metals can be done with sodium, potassium, and aluminium. In all the cases, hydrogen will be released and an alkoxide will be formed. Here, sodium alkoxide is formed. Here, aluminium tertiary butyl alkoxide is formed. Correct? And here, I've taken phenol again and I've tried to react it with sodium and formed a sodium phenoxide, which means what? Even halo alcohols, right? Even phenols are acidic. Even phenols are acidic because they are reacting with metals. Can you see? Phenols and alcohols both are bacha acidic compounds. Both are acidic compounds. ठीक है? Beta, sorry, I didn't see what's your ma'am answer. COH bond cleavage later reaction later reactions are reversed. Is it the reactions are reversed? Reversed in what sense? Bacha, this is a electrophilic attack, that's a nucleophilic attack. The reactions are not reversed. Why are you saying that? Beta, what are you confused, Rudra, in? I am talking about nucleophilic. See, if it is giving away the electrons to this carbocation. It means your oxygen here is behaving as a nucleophile. Nucleophile is what? Something which is electron rich. So it is giving nucleophilic reactions, right? Similarly, this is your alcohol. This is your alcohol, and to this alcohol you have protonated this OH, right? From here you have protonated this OH, and then you have formed what? Then you have formed a kind of negative charge over here. A positive charge over here. And what is happening? Because a positive charge is formed over here, then it is behaving as an electrophilic attack. First is electrophilic in what sense, bacha? No, it is not. This is also correct. Why are you confused in this? This is correct, bacha. This is correct. This will gain a positive charge on the carbon. Okay. So now this already, if I'm positive, what will I will attract electrons? So I will be electron loving. Here the oxygen is getting a negative charge. It means what? I have so many electrons on me. So I will now attract a nucleus. So I am a nucleophile. Okay. So both are correct, bacha. Both are correct. Both are very, very correct. Okay. Somebody is saying very boring. So, bacha, of course, studying, nobody finds studying so much interesting. Like, we're going on since like 4 hours now. Hai? So, nobody finds it so much interesting. That is for sure. That is for sure. Do you want me to sing songs for you now so that you find it interesting? Chalo. What should I do? What should I do? Sing songs? Okay, chalo, let's move forward. I have seen what people are saying to me. Sorry, I get lost sometimes. Sometimes what I'm doing now, if I'm teaching, I just continue to teach. And if I'm looking at the charts, I just keep looking at the charts. So I need to find a balance there. Okay, chalo, reaction of alcohol. We're talking about the cleavage of the OH bond. Remember this. This bond, wherever we're talking about acidity, okay, it is giving away H plus. It means that we are talking about the acidity of alcohols and phenols. Okay, the next case is we can also react the phenol with the NaOH, and we again get the sodium phenoxide. This is again a witness of its acidity, the property of acidity. Now we are going to discuss the acidity of alcohols and phenols. How? This is an alcohol, ROH, right? And there comes a base. Now, what is the property of an acid? The property of an acid is that it easily gives away the H plus ion. And what is the property of a base? That easily accepts the H plus ion. Correct? It easily take away the H plus ion. Hence, due to this, whenever a base is added to an alcohol, what we get a conjugate base and a conjugate acid, which proves that alcohols are actually acidic compounds. Right, next is the acidity of alcohols. Acidity of alcohols, how can you determine? Now I told you that alcohols are acidic. Okay, ma'am, we understood alcohols are acidic because they're giving such reactions because the OH bond is breaking and hence they are releasing H plus, therefore they're behaving as acid. But how do we determine which will be better acid and which will be a bad acid? Okay, so bacha, for acidity order, again I told you, the whichever gives away H plus easily will be the better acid, right? Now, which will give away the H plus easily will depend on the kind of anion formed after the H plus leaves. For example, in this case, in the primary alcohol, after the H plus leaves, this will form a CH2O minus ion, correct? And this will form a CHR2O minus ion, correct? And this will form a CR3O minus ion. Okay, so this is called the conjugate base that is formed after I am doing what? After I have released the H plus. Okay, now which will be the better acid will depend on the stability, of these ions, that are formed after their loss. So which one is the most stable ion? Who can tell me? So, bacha, as we know, the alkyl groups are what? They are the electron releasing groups. They are releasing the electrons. So, if they are releasing the electrons on the oxygen and the oxygen atom already has a negative charge, can you see the oxygen atom already has a negative charge and you have attached electron releasing groups to it. So, what is doing? It is again increasing the electron density more. Hence, it is making the molecule so much unstable. Because what is a stable molecule? When if I already have a negative charge, I want to make it neutral. I don't want to become more and more negative in life, right? I want to become neutral, only and only then I will be stable. Same is the case with this ion. So because you are increasing more electron density by these alkyl groups, hence the acidity order is the primary is more acidic, secondary is even lesser than that, and tertiary is the least acidic alcohol due to this reason. Everybody understood this? Due to this reason, it is the least acidic alcohol. Okay? Acidity of alcohols we discussed. I've already told you about this. Now, bacha, alcohols are weaker acid than water. Please remember this point. They are weaker acid. Why am I saying that? Because, see, this is the base, this is the acid, right? They are weaker acid means what? That when you are trying to react alcohol with water, the water will actually lose the H plus ion. Okay? The water actually loses the H plus ions and not this. And why is that the case? Once again, because RO minus. This is the first case. So R is doing what? The R group of the alcohol is an electron releasing group. Hence, it is decreasing the stability of the anion. Hence, this is a weaker acid. While your water has what? Water has only hydrogens attached to it. Hence, it is a stronger acid compared to the alcohol. Okay? Alcohols can be Bronsted base as well. Or abhi tak I was talking about alcohols act as acid because they give away H plus. But they can also act as Bronsted base. Why am I telling that? Because this is a structure of alcohol, isn't it? This is a structure of alcohol and they have lone pair of electrons. What is a Bronsted base? A Bronsted base is what? A Bronsted base is anything which accepts a H plus ion. So hence these electrons can accept a H plus ion. Hence it can act as a Bronsted base as well. Okay? A Bronsted base as well. Remember this thing. This electron pairs can accept the H plus ion. Hence this is a good Bronsted base as well. Next is acidity of phenols reaction with metal. Again, I just told you that phenols also react with metals and they show the acidic behavior. We just discussed that before. Just like alcohols, phenols also do that. But why phenols are more acidic than alcohol and water? What is the reason behind it? We're going to discuss in this. Why phenols are more acidic? Who can tell me? So, bacha, look at their resonating structure. This is the alcohol. After it loses its H ion, what will happen? This will get a negative charge over here. Now, as I just told you that R group is an electron releasing group. Hence, this is a little less stable compound. Okay? But what happens with your phenol? After it loses the H ion, it will form a phenoxide ion. This is called a phenoxide ion. Okay? It will form a phenoxide ion. And what can this phenoxide ion do, bacha? This phenoxide ion can undergo resonance just like this. And it can form too many resonating structures. This will get a double bond over here. This negative charge will come over here. This will be here. This will be here. Again, I can make so many resonating structures out of this. This negative charge over here. This will come over here. So again, this is O. This will come over here. This will come over here. Right? This will be over here. So can you see that I can make so many resonating structures where the negative charge is rotating inside the ring. Hence, due to this so many resonating structures, the phenoxide ion is much more stable. Hence, phenols are more acidic than alcohols and water as well. Okay? Now, what is the acidity order? That H2O is more acidic than your, that your phenols is more acidic than H2O and then is your alcohol, right? This is the acidity order. Always follow this acidity. Phenols are the most acidic, then is your water molecule, and then is your ROH group. This is the acidity order. Beta, Bronsted base. Yes, Bronsted base is anything which can accept a pair of H plus ion. Okay? Beta, the thing that you're talking about, lone pair. Lone pair are actually in Lewis bases. Okay? Every Lewis base will have a lone pair. But a Bronsted base is something which has the ability to accept H plus. Right? So this is a basic difference between all these things. Beta, basically, it's not important that they have a lone pair in it. They should have the tendency to accept H plus. Could be anything. Could be anything. Mostly they do have a lone pair. It's not necessary. But Lewis bases will definitely have a lone pair. ठीक है? ठीक है? Beta, I will be taking amines today at 9 p.m. now because this session is already extended so much. So I will take a little break. I will have my dinner and then I will come back at 9. This session has shifted at 9, but we're going to study all-nighter. Why can't we do that? We'll pull out an all-nighter. We're going to study all the aldehydes, ketones and amines tonight. Tonight, TK, everybody can come tonight at 9 p.m. If you are there, then I will be here as well. Next. So this is why, because there's so many resonating structures of phenol, as you can see, that is why they are more acidic than alcohols and H2O. Next is, but the phenoxide ion that we formed is even more stable than the phenol. This is a very important point. People just do not focus on this point. The phenoxide ion is this. The O- ion that is on the benzene ring is more stable than phenol. Remember this. Phenol structure is this. Now, if I draw the resonating structures in each cases, can you find that how many resonating structure phenoxide ion has? It has 1, 2, 3, 4, 5 resonating structures, and the phenol. This and the below one are the resonating structures of phenol. Remember this. So here I have drawn the resonating structure of phenoxide ion. Below it are the resonating structure of phenol. Correct. And here, what else can you see? What else can you see for phenol? It also have 1, 2, 3, 4, 5. So you'll be like, ma'am, they both have 5 resonating structures each. How can you decide that phenoxide ion is more stable than phenol? So, bacha, I will tell you one more thing. In the phenol, this is the phenol. Okay, this is phenol, the downward. So, bacha, in phenol, can you see that the oxygen is getting a positive charge in its resonating structure? And there is a charge separation happening. See, positive, negative, positive, negative, positive, negative, right? So, in the phenol, whenever I'm drawing resonating structures of phenol, I'm getting a charge separation. And whenever charge separation happens, it destabilizes the species, right? So, charge separation should not be there. Also, your more electronegative oxygen is getting a positive charge, which is not good for stability. Hence, phenoxide ion is more stable than phenol. Another important point that can be asked in your exam. Okay? Next, electron withdrawing groups increase the acidity. We're talking about the acidity here, right? For example, this is the phenol group. This is the phenol that I have made, right? And if I've attached any electron withdrawing group to it, for example, NO2 I've attached. Now, after losing the H plus, it will form a phenoxide ion just like this, right? Just like this. So, if I attach any group which has the capacity to actually reduce the negative charge on the ring, then it will do what? It is stabilizing the species, right? Because I want to reduce the negative charge. I want to become neutral in order to become stable. Hence, electron withdrawing group will obviously always increase the acidity. Everybody understood this? Everybody understood this? Next, acidity of phenols. For example, this is given over here, ortho, meta, para, nitrophenols. Which one will be more acidic? Which one will be least acidic? Who can tell me? Between ortho, meta and para, which one will be more acidic? So probably I'm going to write over here. For example, this is the alcohol and this is the NO2 group over here, right? And here it is again, I have made another thing. Here is the alcohol, and here I've made a orthoisomer, and here I have made a meta isomer. Okay. Now we're talking about the acidity order. Okay, bacha. So the most acidic will be the para isomer. Para isomer. Why? Why? Because here the NO2 group. Here in the NO2 group, what is happening? What are the two effects that the NO2 group shows? The NO2 group is an electron withdrawing group. It shows a minus I effect as well as a minus R effect. Right? At the para position, both these effects are possible. At the ortho position, only minus I effect is possible, and again at the this meta position, again only and only which minus I effect is less. Right, here minus I effect is a little less, because inductive effect is bacha based on what? The inductive effect is actually based on the distance. As the distance increases, inductive effect decreases. Hence, this is the order for the acidity of phenols. Always remember this. Para, ortho and meta for the acidity. Okay? It shows both. Minus I is electron withdrawing group. Minus R is because it is showing that resonating structures. Okay? It shows resonating structures. It only, and minus R is shown only and only at para positions. Whenever you have things to compare, then only and only show resonating structures at the para position. Okay? Yes, bacha, pK is used to measure the acidity. Here the pK is written. Okay? pK is used to measure the acidity. Just remember one thing, that pKa value is inversely proportional to acidity. Okay? It means higher will be the pKa, lower will be the acidity, or lower will be the pKa, higher will be the acidity. Can you see between these things? Between ortho, meta and para, the para isomer has the lowest pKa, it means it has the highest acidity. Then it's the ortho isomer, then it is the meta isomer. Okay? Similarly for cresol, what is the structure of cresol, bacha? This is the structure of cresol. This is your OH group over here, and here it will be your CH3 group over here. This is the cresol group. Ab cresol can be ortho. This is the ortho cresol that I've made here. And again it can be a meta cresol just like this. Okay? And again there can be a para cresol. Now cresol is doing what? This is increasing the electron density. Hence it will decrease the what, bacha? It will decrease your acidity. So cresols are not good acidic things. Now in this is a very interesting thing that you'll see, that phenol's pKa value is around 10, that is given here, while ethanol's pKa value is given 15.9. As I just told you, higher the pKa value, lower the acidity. It means ethanol is very much lower acid than phenol, and data wise speaking, phenol is a million times more acidic than your ethanol. Remember this, million times more acidic than your ethanol. Okay? Beta, mesomeric effect, somebody is asking me, ma'am, please tell. Okay, I'll tell it here, mesomeric effect. See, for example, this is the benzene ring. Okay? I've made, beta, I'm explaining mesomeric effect, somebody has asked, that is why. And for example, I've attached the NO2 group over here. So NO2 group looks something like this. Okay? Now NO2 group is a what kind of group? It is a electron withdrawing group. So what it will do? It will start withdrawing electrons from the benzene ring. So what it will do, for example, this double bond will get transported over here, and this double bond will get transported over here. So this kind of resonating structure would be formed. See, this kind of, so here double bond N, here it will be O negative, here it will be O again, and here it will be here and here, and this will get somewhat of positive charge over here. Okay? So what are we doing? We are withdrawing the electrons from the ring. So again you can form a resonating structure. This will again go here, right? So again I can form a resonating structure like this. This will be N, and it will be O negative. ठीक है, here this will come over here, so the positive charge now comes over here, this will be over here. Again in the next resonating structure you can keep making these resonating structures. So this effect is called bacha the mesomeric effect. Mesomeric effect or the resonance effect are exactly the same things. They do what? Whenever you make these kind of resonating structure, if the electron withdrawing group, they will withdraw the electrons. If they're electron releasing groups, then you can do what? You can, for example, how in haloarenes I show you, right? In haloarenes, they were showing plus R effect or plus M effect. This is the minus M effect or the minus R effect, one and the same thing. You can even show plus M effect. For example, something which is rich in electrons will give its electron to the ring, increasing the electron density in the ring, and it will form a double bond over here, right? And here what will happen? This will become a negative charge over here. This gets a negative charge. This will come over here, right? So what you are doing here, this now you are increasing the electron density in the ring. So this is a plus M effect or a plus R effect. So both of these kind of effects are same. Either you can call it resonating effect or a mesomeric effect. It can be electron withdrawing or it can be electron releasing. But in both the cases, so many of the resonating structures will be formed. Those are the effect. Okay, everybody understood? Beta, those are the same thing. Those are the name of the same thing. Mesomeric resonance are the same effect. Same effect. Plus M plus R are the same thing. Okay, everybody understood? Next, esterification reaction. So we can form esters. We have been forming esters since our 9th class, 10th class. What do? We take a carboxylic acid, try to react it with the alcohol in presence of H plus ion and form an ester. That's what we're doing here. Again, you can form an ester using a carboxylic acid or using an anhydride or using a carbonyl chloride. In all of these cases, you can form ester, and in carbonyl chloride, just that you use a base because HCl is formed, so you need to neutralize that HCl so that reaction can move in the forward direction. Next, esterification, best example is this how the aspirin, which is the medicine for your headache, that is formed. You take salicylic acid and you take acid anhydride. As we know, acid anhydride and your alcohol can react together to form an ester, and they form an acetyl salicylic acid, which is called aspirin and acetic acid. Again, a very important reaction. Okay, now we are back to the reactions involving CO bond. Okay, this CO bond will now cleave. Now the reactions involving CO bond only takes place in alcohols, right? Like the phenols were showing acidic character, hence the OH bond was breaking in them. But the CO bond does not break in phenols. Okay, except there is one exception. The CO bond breaks in phenols only and only when they react with zinc. Otherwise, CO bond in phenols never break, only OH bond in phenols break. Why is that the case? Again, extremely important and crucial observation. For example, here is the OH. Right, this is the benzene ring. So what will this OH do? This oxygen has lone pairs. So it will donate its lone pair here, and here it can form resonating structures like this. Right? What it is doing, it is forming so many resonating structures just like this. And here it will gain a negative charge, here, right? Here again, it will just go there. And then here it will come here again. So I'm forming too many resonating structures. But the one thing that you should notice is that this bond is actually getting a partial double bond character. Can everybody see? A partial double bond character is given to the COH bond, right? The CO bond is getting a partial double bond character. Hence, it is difficult to break. Hence, CO bond does not break in phenols. It only breaks in alcohols. Only alcohols show this type of reaction. First reaction is a reaction with hydrogen halides that you can see with ROH, HX, and you can form RX and H2O. Right? You can form this reaction with hydrogen halides. Next is the Lucas test, but very important. Very important. Here what happens? This is a very important test for testing, for distinguishing between primary alcohols, secondary alcohols, and tertiary alcohols. Very important reaction to distinguish between all these three. right? For example, primary alcohol in presence of ZnCl2 and HCl, no reaction or slow reaction occurs. In presence of secondary alcohol, again this kind of reaction occurs, and tertiary chlorides are again formed. So alkyl chlorides are formed in secondary and tertiary alcohol case, but with primary alcohol, no alkyl halides are formed. Okay? No alkyl halides are formed. It means that the reaction 2 will show no turbidity. No turbidity will be shown. So for example, you took a primary alcohol and you reacted with HCl and ZnCl. Okay? You try to react. Beta, I'm doing just that only. Within one day, I'm trying to complete all your organic chemistry portion. At least I'm really tired right now. Sorry about that. But we will gain back the energy. Hi guys. So for the primary alcohol, what you're trying to do, you took the primary alcohol, reacted with HCl, ZnCl2. These are called Lucas reagent. HCl, ZnCl2, Lucas reagent. And primary alcohols show no reaction with Lucas reagent, which means that these alcohols, remember one thing, alcohols are soluble in Lucas reagent. Okay? But after the reactions, they sometimes form alkyl halides. Those alkyl halides are not soluble in Lucas reagent. Hence, they precipitate down. So, this will precipitate down. So, what happens with primary alcohol? We get no precipitate. Okay? We get a precipitate only after we heat it. Okay? Secondary alcohol, we get a precipitate, but we get a precipitate after 10 minutes. For example, 5 to 10 minutes. After 5 to 10 minutes, you get a precipitate. With tertiary alcohol, you get a precipitate instantly. Immediately, you get a precipitate with tertiary alcohol. So, this is how we can distinguish between three kinds of alcohols using the Lucas reagent. Okay? Next is Lucas test mechanism is like this. For example, here carbocation is formed. So can you say the Lucas test mechanism is a SN1 mechanism because the carbocation is formed. Okay, carbocation is formed. Next is reaction of alcohols. Reaction with phosphorus stylites. This we have already discussed, bacha, with phosphorus stylites, right? While we're reading the haloalkanes, haloarenes. So I'm not going to discuss it again. Next is dehydration reaction. Very important. Even its mechanism is very important. This is the only kind of mechanism that can be asked in your exams. Okay? Dehydration means what? Whenever whenever you take an alcohol and you try to heat it in presence of acid, then the H2O molecule will leave and it forms a double bond just like this. Okay? Similarly, ethanol forms a ethene, right? And you can even undergo secondary and tertiary alcohols are dehydrated under milder conditions. So ethanol, which is a primary alcohol, so you need like drastic 443 Kelvin in order to dehydrate it, in order to remove water molecules from it. But for secondary and tertiary, you need milder conditions, and then also alkenes will be formed. Remember this thing, alkenes will be formed. Okay? Now next, dehydration. Again, the ease of dehydration of alcohol depends on the following order: tertiary, secondary, primary. Means what? Which has beta bus, it's going to be completed. It is going to be completed. Thus, the relative ease of hydration is tertiary, secondary, primary. Tertiary alcohols are much easier to dehydrate than secondary and then primary. Remember this thing. This is the mechanism, bacha. Please focus on the mechanism. What is happening? The lone pair on the oxygen attacks the H plus from the acid and forms a hydronium ion. Just like this, protonated alcohol is formed. Now, because H2O plus is a very good leaving reagent, so it leaves from here and it forms a carbocation, which is a slow step, which means it can decide. Here you can decide, here you can do rearrangements of the carbocation, right? And then the last is because we use the H plus here. So again the H plus is given away back in the reaction because H plus was a catalyst, and you get a ethene. Afterwards you get a what kind of 𝐳𝐸 product? Ethene you get. 𝐳𝐸 is what? More substituted alkene you get. Next is involving the oxidation of the alcohol. So when you oxidize alcohol, what do you get? You either get aldehyde, ketone or carboxylic acid depending on the oxidizing agent you are using, right? For example, if you are using the oxidation, for example, I just used alcohol and I oxidized it. The first oxidation product is an aldehyde. The second is a carboxylic acid, right? But it depends on the oxidizing agent. If it is very strong oxidizing agent, you can directly oxidize alcohol to acids. If it is a mild oxidizing agent, then you can oxidize it to aldehyde or a ketone. Okay? For example, PCC is a very mild oxidizing agent which oxidizes alcohols to aldehydes. Similarly, your CrO3 is again a mild oxidizing agent. It oxidizes primary alcohol to aldehydes and secondary alcohols to ketones. Remember this thing, primary to aldehydes, secondary to ketones, right? And similarly, oxidation can occur in presence of copper at higher temperature. What is happening? You just took an alcohol and then made it into aldehyde, and then you take a, so primary is converting into aldehyde again, and secondary alcohol is converting into a ketone. Tertiary alcohol never oxidizes. Remember this thing, tertiary alcohol do not oxidize. Do not oxidize. What happens to tertiary alcohol instead? They instead form alkenes. Elimination reactions happen. So tertiary alcohol never ever oxidize them, just form alkenes out of them. Just remember this thing. Okay, oxidizing agent example, bachcha, KMnO4. I'm giving you example only na. This is a strong oxidizing agent. KMnO4, K2Cr2O7, strong oxidizing agent which oxidizes alcohols directly to acids. Mild oxidizing agent, for example, I just told you, PCC, CrO3, even copper, these are mild oxidizing agents which are not directly converting alcohols to acids. Either they're converting alcohols to aldehydes or ketones. Understood this? Now reactions involving the cleavage of CO bond. CO bond, another oxidation. This is a very, very good pointer that is given in your NCERT. What is written over here? They have told you that sometimes the alcohol that we consume is what formula? That is the ethanol. But sometimes that ethanol gets mixed with a poison which is a methanol. Then what happens to your body and how it is cured? All of this is written in this paragraph. Please read it. Extremely important paragraph. Okay. Now phenols show electrophilic aromatic substitution reactions. Okay. So please go through these kind of reactions, which are extremely important. We are just going to complete everything. So electrophilic aromatic substitution. So this is the phenol. This is how your phenol looks like. Phenol has a OH group on it, right? OH is what kind of group? OH is plus I group. It donates the electron. Also, OH is a plus R group. Hence, it is a very, very activating group. Activating group means what? Any group which is attached to the benzene ring, which increases the electron density inside the ring. Which increases the electron density inside the ring is called the activating group. Remember this. That is called the activating group. Okay? Plus I, plus R. Everybody understood this? Okay? Now, what all are the electrophilic aromatic substitution reactions that can go on? For example, with phenol dilute HNO3, the electrophile here is NO2 plus, and because OH is, again I will let you know here, it is ortho and para directing. Remember this. So ortho para products are formed. Para is obviously the major product. Similarly, because both ortho and para products are formed, then how to separate that, ma'am? Both are formed. Then they can be separated very easily because both of them have very, very different boiling points. They can be separated easily through steam distillation. Why? Because here, can you see that the ortho isomer only has intramolecular hydrogen bonding, while the para isomer has intermolecular hydrogen bonding, and we all know that intermolecular hydrogen bonding is stronger than intra, right? Intermolecular is stronger than intra. Hence, the boiling point of para will be more than the ortho. right? Boiling point of para will be more than ortho. Hence, ortho is what? Hence, ortho is very, very evaporizable, right? It has low volatility, low volatile. It means it will quickly become vapor and we can quickly separate these two products. Next is nitration. Once again, we can also nitrate the entire ring. If we use concentrated HNO3, we can get 2,4,6-nitrophenol, which is a picric acid product. Again, that picric acid here, right now, the current method of formation of picric acid is this. Please look at this mechanism because it is given in your NCERT, not directly, but in the form of a statement. So I have attached the reaction here as well. Please go through this reaction as well. Next is write the structures of major products expected from the following. Mononitration of 3-methyl-phenol. Please answer this question. Use it as homework. Whatever questions I've mentioned here now are the important questions that you have to solve. Even if you do not have time right now, please solve these questions which are attached in the PDF which you will get on the Telegram channel. Okay? Next is halogenation. The halogenation reactions again, when we react Br2 with CS2 or in any non-polar solvent like CHCl3, any non-polar solvent, then again Br gets attached on the ortho and the para positions, right? So we have discussed the halogenation. This is the another kind of halogenation. If I'm using what? I'm using too many molecules of Br2. Next is Kolbe's reaction. Again, important name reaction. What do you do in Kolbe's? You take a phenol, react it with sodium hydroxide. So form a sodium phenoxide. Then react with CO2 in presence of acid. So, bacha, the sodium phenoxide is even more reactive than phenol. Remember this thing. Even more reactive. This sodium phenoxide more reactive than phenol. And can you see that a mild, this is what? This is a very mild electrophile. This is a very, very weak electrophile. I'll not write mild. I should write is a very weak. CO2 is a very weak electrophile and still we can form salicylic acid after we have converted the phenol to the phenoxide ion. ठीक है, Kolbe's reaction, very, very important. And remember that the phenoxide is more reactive than phenol. Reimer-Tiemann reaction, ask time and again. You just cannot afford to miss this reaction. What happens? You use a phenol, the reagent are chloroform in any base. It could be aqueous NaOH or KOH. Then you form an intermediate just like this, right? And then you react it with another base and you form a phenoxide ion. Then you react it with acid and you form a salicylaldehyde. Very important reaction to form salicylaldehyde from just phenol. Reimer-Tiemann, asked time and again, even in your JEE exams or your boards exam. Very, very important. It will be asked, for sure will be asked. Next is reaction of phenol with zinc dust. With zinc dust, how do you react phenol? So I told you that the only reaction of phenol where this CO bond breaks, the only reaction is this where the CO bond breaks. Otherwise, only the OH bond was breaking. So here when I react with zinc, I get a simple benzene ring. Next is oxidation. When you try to oxidize your phenol, what do you get? You get a benzoquinone-like product over here. So this was the last reaction from my side from alcohols and phenols. ठीक है? Beta, I will try to teach today. Otherwise, obviously, if today doesn't happen, tomorrow, for sure, it will happen. Depends on my energy. Let me just go eat and grab something. I will try to come in night, for example, at 9 p.m. Or if I don't want to exert myself even more, I will come tomorrow because we still have one more day, right? We can do one more day. We can do a long marathon session just like this. If you're with me, then we will perfectly, definitely do that. Thank you so much for attending this session. Thank you. And I will see you probably today at 9 p.m. And please like the session, subscribe to the channel if you're not subscribed yet. And we will meet again. Thank you. Signing off.